We start now?
Yeah.
All right, cool. So let's start then. Good afternoon or good morning, everybody. So it's a lot of pressure talking to you guys. So yesterday we went over this skeletal reduction, right? A lot of sense as background introduction. So today, I guess it's Friday. Friday for
Friday.
most people, I guess.
Yeah.
Friday afternoon here. So it's a time to relax a little bit. So I deliberately left some equation today, right? So for everybody to enjoy. Just kidding. So today we want first topic we want to talk about is about timescale based reduction. So timescale based reduction is quite a different thing from what we did yesterday about skeletal reduction. Skeletal reduction is basically something it's really difficult to mess up because after validation, if you develop a reduced model, if everything shows up well, and then it's a working model, right? But timescale based reduction, it keeps on giving issues. So that's a lot more complicated topic, and it frequently involve a lot of math. So some methods, it's kind of very complicated to discuss or to really, if you want to understand it clearly. So there are many equations we need to go over. So in terms of equations, I guess for model reduction, it's a little bit different from what we do for many other subjects. Because for model reduction, it's more similar to debugging a program, to writing program. So we want to try to figure out if there's any issues with the model, right? Because if there's nothing with the model, we are fine. But we want to figure out where the models has problems and where it can give you large errors, for example. So basically, we want to find where there are problems. So not like many subjects, we want to find out where actually it works well or you show good results. So frequently, if you read a paper, I guess in combustion literature, if you read the paper, the chances you see a method was reported or a systematic equation is reported. And then a lot of examples show how good it is, how well it is. And you rarely see people talking about like where you have problem. This is not good, that is not good. It's not very pleasant, right? Overall, I guess if you tell people that your method or your result have issues, it's problematic here. So people get offended easily. So that's something that's kind of interesting for model reduction, as we are born in a discipline that want to try to find bad things. Okay, in this sense, actually, so you will probably, if you work on model reduction for a long enough time, you will have a lot of things you realize there are issues here. So to make it simple, like for example, the simplest reduced model, the one-step reaction, right? So what's wrong with one-step reaction? So one-step reaction, we all know it has this feel-good product, right? With one reaction rate, which is K, you specify three parameters, right? K is equal to some kind of Arrhenius form. You specify what A is, what N is, what E is. So three parameters, pretty much you can use to fit some targets, 1, 2, or 3 selected targets you want, and make flame speed correct, or sometimes ignition delay correct. And then after we look at the properties for detailed chemistry, we figure out why the one-step chemistry always has problems, why it always give you issues, right? And for example, we assume activation energy is large because we all know combustion activation energy is a large E problem. But then if you look at detailed chemistry, we get two things. One is if you want to ignite it, it needs to have a radical pull. If you don't have the radical pull in the beginning, it's something called auto-ignition. So the chain branching process actually controls the rate for the combustion process or ignition process. And that activation energy give you the slope in the ignition delay plot, okay? That's pretty large. So ignition chemistry is controlled by quite large activation energy. But once you have a flame established, it's strongly burning, you already have a radical pool there, right? It's burning strongly, then, and you know what radical does to combustion system. So the people working on chemistry says combustion is a self-catalytic process. It means once you have the radical pool built up, your activation energy almost goes zero. So in continuous flow reactors, the activation energy effective is nearly zero or very small. So that's actually contradicts with what we assume in a lot of combustion theories, assuming large activation energy. So for example, if you have an S curve, if you get a large activation, then you find actually S curve top should be, upper branch should be almost flat, right? And turning point should be almost like a pike, like a needle, because all the reaction, it should be concentrated near the highest temperature, right? And this should be what the S curve will look like. But if you have what happens to hydrogen, and it looks like almost like this, okay? So it's big head here. So obviously, reactions spread it at different temperatures. Why that is because there's a radical. Once you have a radical, so radical can, in a radical serves as a little magnet. So why? Because you lose ampere electron. So you put dot here, right? So what is dot? Dot is like spinning electron. The spinning electron give you magnets. Okay, so magnet. So basically, you have one magnet here, and if you come close to two things, this is a stable molecule with two parts. For example, H with another C or R, we call it R, and this guy can stick together, and naturally it splits to give you chemical reaction. Okay, so therefore, if you have a radical there, you don't really need to hammer or have strong collision with the molecule to get a reaction going on. So therefore, with radical pool established, it's a low activation energy problem. Naturally, then with one step of chemistry, you cannot possibly capture this entire S curve behavior. So both low temperature ignition process and high temperature flame chemistry. So there must be something losing. And if you think a little bit more, so if you want to come up with a few steps, how can you make it up? Like for example, low temperature, you can assume one step controls the radical branching, right? High temperature near extinction, if you get an S curve near extinction, you get a, so near extinction mostly it's a CO formation. If you get a hydrocarbon, form CO from CO plus, so whatever HCO or formaldehyde, so it goes around eventually to form CO, HCO. So CO formation is very fast. That's why it can react very fast within a very short time. But then you don't have time to form CO2 because CO2 formation from CO, it takes much longer time. Okay, a reaction like this, it takes about a milliseconds or longer. Okay, much larger than the time scale for CO formation, which is 10 microsecond, 100 microsecond. So order of magnitude faster. So therefore, if you want to put together a reasonable reduced model, so at least you need 3 steps, right? So radical pool build up, CO formation, CO2 formation. 3 steps is really the minimum I can think of. So including the model tuning, but you cannot really simplify it to one step. And then similarly, if you assume just one step reaction with large activation energy, no matter how you play the math, like a large activation, symptotics, whatever, you will miss something. Okay, just keep it in mind. That's one example. And then for timescale based reduction, so we are dealing with similar issues here. So here I want to talk about 3 things. So timescale based reduction is filled with math. Some of the math probably is even more scary than symptotics. Okay, it's the large activation energy expansion, because you always heard about it. For example, in timescale analysis, probably the pro on the cron is called computational singular perturbation, CSP, right? It's a singular perturbation. In other words, it's also a symptotic analysis. So mathematically, it's almost like it's equivalently difficult to handle. But then, so if we want to get working reduced model based on timescale analysis. So we really need to figure out, so physically or actually what is happening here in the system with fast things, with slow things, and what math do we have to deal with? What math we probably can avoid? We don't have to go through some of the things. So here this section, it serves as a purpose of similar to debugging process. We want to look at the benefit and issues in each different method to see if you want to use this method, what you need to be careful with and what may or may not give you what you want. Okay, so let's focus on three things. So one is we got the linear problem. When you study linear algebra, you have the system of ordinary differential equations, ODEs, right? We have the eigenvalue decomposition method, try to solve the linear ODEs. We all have we will show briefly how you go through it. And then for chemical reaction system, we know it's more or less always have some kind of nonlinear features there. And we call it nonlinear problem. And then once you have a nonlinear problem going on, the math become always more complex and annoying to handle. And then we are dealing with two very prominent methods. One is called intrinsic low-dimensional manifold, ILDM, and CSP. In many cases, people are scared about this method. So they look at these papers. Some of the papers are written in very complex notations or explanations very, very complex. So when the math getting very complex, so first of all, we want to have some difficult math in our papers or talks, right? Just to appear maybe better educated, so to scare people off. And then on the other hand, so there's a side effect if you have a lot of complicated math. First of all, it's become more difficult to understand, right? A lot of people, if cannot figure it out, they get scared away anyway. And then another side effect is if you get a complex math, you can probably, some problem will be more difficult to find. It's like it's just you have bugs buried in the long code. If you get 10,000 lines of computer code, if you find a little bug in it, it's very difficult, it takes a lot of time. But if you have a much simpler program with 100 lines, it's a lot easier to find where the bug is buried, right? So in this sense, if possible at all, so I would prefer to use very simple math to make sure we don't overcomplex our method or theories. So more people can understand it, and then we can more easily to find where we can have issues, or another benefit is we can probably understand the features or properties for this method better. Okay, so now let's first look at the first thing, what we learned in linear algebra. So if you study linear algebra, or I guess college math, so they always tell you how to solve linear ODEs, right? Linear ODE basically is something like this. If you have a dependent variable as function of matrix time the variable, right? So G, by the way, it's a vector with whatever you want to solve. It's called dependent variables. Jacobian, so a lot of cases we write dy dt is a matrix A times y. It's just keep on stuck. Okay, so this is probably a more frequent used notation, but here, because we want to compare the three different methods, we just use different symbols. Okay, dg dt, some kind of constant Jacobian matrix times the variable itself. If you think how to solve this one, because you get a multi-variable involved, each variable can change with different time scales, right? Some variable can change fast, some variable can change slow, some variable decays to some small value, some variable may explode and to become some kind of large number. All this, if you want to solve it, what you can do is you can use the standard eigendecomposition, something called eigenvalues, an eigenvector. So eigenvector is defined this way, right? So B time so B is a row vector. Okay, we call it left eigenvalue because if you multiply a row vector to the left of the matrix, it gets lambda's eigenvalue times B itself. So once you have a pair of B and the lambda satisfy this definition, we call this an eigenvector and eigenvalue. So the definition is standard in linear algebra. So in most cases in linear algebra, we deal with this so-called right eigenvectors, A, which is so this is typically we call eigenvector. It's a column, right? If you multiply this column to the right side of the Jacobian, that's called a right eigenvector. So basically, it's equal to lambda times A. And if you put all the B's together, so B1, B2, B3, you get the matrix, and you get to put all the A together. You get A1, A2, A, and so this matrix in linear algebra is called eigenvector matrix. And this matrix, so we denote this to be matrix A. Okay, this matrix we denote to be B. So in that case, B and A, it's just inverse of each other. So it's like previously in linear algebra, typically we use eigenvector matrix to be V, and the left eigenvector, which just to take the inverse for it, just to sort of some confusion about the notation. Okay, but anyway, it's eigenvector and eigenvalues. So suppose you can identify one eigenvector with some special lambda. If lambda is a large negative number, if lambda is large negative number, what happens here is if you do dot product of B to the left hand side for the ODE. Remember the ODE is dg dt is g times g. You do the B to both left and the right hand side. The left hand side become this. You can just move this B to into this, right? Because for linear system, the Jacobian and its eigenvector are all constant. You can just move it, and the B dot G give you, it's a dot product for this thing. And this result for dot product will be a scalar. And we can denote this to be so-called F. And in linear algebra, there's a very fancy name for it. It's called a mode. You already probably heard about this jargon. Okay, the mode, some mathematical jargon just to make it appear very, very intelligent. Okay, so mode is a scalar, but it's just linear combination for all the different variables. Somehow you get this combination, the right hand side for this one. If you do B dot G dot this one, you can look at B dot G is what? Based on the definition for eigenvector, eigenvalue, you can B dot G is equal to the eigenvalue times the eigenvector, right? And then you get this B and G together, it give you equal to lambda F. And your equation reduces to some very nice form, which is decoupled from everything else. So df dt is lambda F. And you already know the solution for this equation, right? It's exponential. So basically, F equal to some kind of constant. This constant is determined by so-called initial condition, what its value is, and the initial is basically B times G 0. So the initial concentrations or initial values for the dependent variable, so dot product with B give you F0. Okay, and then there is an exponential term, e to the lambda t. So if lambda is positive, what will happen to it? If lambda is positive, this is exponential growth, right? And if lambda is negative, what will happen? That will exponential decay, right? So therefore, this mode has two very distinctive behavior. For positive lambdas, you get this exponential growth behavior. This is called explosive behavior. So any exponential growing process is called explosive behavior. Okay, and if lambda is negative, F will decay exponentially, approaching 0, and this is called a decaying process. And once it becomes almost 0, people call this mode becoming exhausted. Exhausted is another jargon saying this mode approaches 0. Okay. Well, once it's equal to 0, then so when this mode decays almost 0, you can write down something like an algebraic equation. So B dot G equal to 0 or approximately equal to 0. So this equation can actually link several different variables. For example, if you have species concentrations in the equation, it can give you a relationship between some species with something else. Okay, and this algebraic equation, it can be used to solve for some variables without dealing with the ODEs. But you have to assume this guy f has decayed to 0 already. So how can you make sure f is almost always stays 0? One way is if you look at the lambda. If lambda, the magnitude for lambda tell you how fast it goes, right? Because lambda over t over 1 over lambda. So basically, 1 over lambda typically on the bottom give you the time scale. Suppose 1 over lambda is 1 millisecond, so that means every millisecond your value changed by factor e, right? So therefore, lambda, people call it, although it's eigenvalue, but physically, if you do 1 over lambda or reciprocal for reciprocal lambda, people call it characteristic time for the mode. It tells how fast this mode decays or explodes. So that's the terminologies we want to get familiar. And if you get a linear system, and if you get a large negative lambda, so that means this guy will decay, will dive quickly to 0 in very short time. So if you skip the very short beginning time, the remaining time, the smooth always stays 0. Okay, and this would become a good approximation for almost everywhere here, the majority of the time domain, except the very early, called transient period. People call it transient initial period. So if you don't care about what happened in the first, let's see, microsecond or whatever, you can skip this second and then take care of everything else with quite a good accuracy. Okay, so this is what happens and what we learn in linear algebra. So eigenmode, eigenvector, eigenvalue, which is a reciprocal time scale. So, and then positive or negative eigenvalues tell you whether it's explosive mode or it's decaying mode. Okay, and this terminology is one way to figure this out. So if you have a linear or approximately linear system, you can just take advantage of this equations. Okay, so for example, you can just solve this equation together with the remaining ODEs. So how to solve them, that's a more complicated story. But a lot of people believe solving this so-called DAE system. DAE system means differential algebraic equation system, okay? Rather than ODE system. ODE means each equation is a differential equation. A lot of people believe solving DAEs can be easier than ODEs. It may or may not be true. Sometimes solving DAEs can be more difficult than ODEs. And in many cases of combustion simulation, actually it's more complicated to solve DAEs rather than solve ODEs. Because ODEs can actually, in many cases, can solve more easily than DAEs. So upfront in the beginning, we already have some issues with timescale analysis. We see we approximate fast modes decays to 0 quickly. We obtain an algebraic equation, and this equation, it's good in terms of mathematics, right? But sometimes it's useful, sometimes may not be that useful. Okay, let's see what else can we learn from this one. So in some situations, you will find the eigenvalues or eigenvector become complex numbers. If you do MATLAB, do decomposition for some random matrix, frequently you will find some eigenvalues and eigenvectors are complex numbers. If they are complex numbers, if lambda, for example, and b are complex numbers, you go through everything and you expand the real part, the imaginary part, you put them together, you find the solution. Actually, each complex eigenvalue will give you a pair of mode. The real part give you one thing, the imaginary part give you another thing. So each mode, by the way, R means real part, I means imaginary part. Okay, each part actually contains two terms. One term is if you look, this guy is the same as this guy. Okay, and this guy is the same as this guy. So basically, there are two terms playing around, and the two modes are coupled or mixed two terms. So therefore, if you get a complex eigenvector, you can really decouple all the modes. So there are two modes always interact with each other. Okay, why? Because they are oscillating mode. If you look at what happens here, so the real part here, you get an exponential part if lambda r, which is real part of the eigenvalue is positive, this portion will explode, right? If lambda r, or the real part of our eigenvalue, is negative, this term will decay, right? Just similar as what we learned from real eigenvalues. And this term, sine and cosine, give you oscillations. So if you multiply these two terms together, you will find in reality some mode it oscillatory decay. Okay, the magnitude becomes smaller exponentially, but it oscillates. So the oscillation was from the sine cosine term, and the decaying from the exponential term. Okay, so it's a little bit complicated, but when you deal with chemistry, you will find sometimes your system is stable, it doesn't oscillate. Sometimes it oscillates. So frequently you find flames and the system or reactor, it give you oscillation. Well, it may be induced by chemistry source term, maybe induced by mixing terms. But so oscillation sometimes give you combustion instability. So this is one sort of instability. Okay, but if you get this growing stuff, if the instability grows, that's really something concerns a lot of people. So in engines, for example, you don't want to become unstable, right? Difficult to control. So for example, combustion instability can grow if you get a positive real part for the eigenvalue. In a lot of stability analysis, we want to look at this complex eigenvalues that give you a lot of good idea. But for model reduction purpose, we probably don't care too much about this one. It's not that useful to reduce the system, but this case we can still use it, right? If you have a large negative real part for the eigenvalue, this guy is still decay very quickly. It decays to zero very quickly, but it's still oscillating, right? We don't care too much about oscillation because after initial transient period, you can always approximate this guy equal to zero, just like we did for the real numbers. Okay, so therefore, in general cases, if you have a linear system or you have approximately linear system, you can always look at the eigenvalues for Jacobian. If you get a large negative eigenvalues, it gives you a very good so-called quasi-steady state approximation, the chance to get an algebraic equation like this, rather than solving differential equations. Okay, and that's pretty much. We all learned this in linear algebra classes, so there's nothing serious about this. But if you deal with real life stuff, if you do real life chemistry, then you know the thing is not a linear problem, right? For example, if you write down the reacting system, so dy dt, y is concentration and temperature, maybe some time you include pressure, and G is chemical reaction source term. Let's see if we are dealing with autoignition. So dy dt is omega y. So G is the chemical reaction rate, right? How you can convert this to a linear, almost like linear form, you take the chain rule. So what you do is you do dg dt is like here. Then you use the chain rule to make dg. G only reaction rate depend on concentrations, right? Once you know concentration, you can know the reaction rate. So you can do dg dy first and then do dy dt. So that's chain rule. And dg dy, people call it is the Jacobian matrix. That's the Jacobian matrix. So if the Jacobian matrix has the form of partial gi or partial yg, right? So this is the ith row and the jth column for the Jacobian matrix. It's a tedious differentiation. It looks like almost like the same format than what we did before. dg dt g times Jacobian. If you compare with the linear case, the format is the same. And what if we multiply the eigenvector for Jacobian to the whole equation? So what will happen? So this is left hand side. This is right hand side for the equation. Okay, you find the right hand side the same. It give you lambda times eigenvector because b times Jacobian give you lambda b based on the definition for eigenvector eigenvalues, right? So the right hand side give you lambda bj. You can call this lambda f if you want. You can still see f equal to bg. Okay, but the left hand side, the trick thing is because b is eigenvector for Jacobian, and Jacobian can be function of temperature, can be function of because it has the reaction rate involved. It can be function of species concentration even. So it's time dependent. So therefore, you cannot just put it be inside dd term. So you cannot move it in. And if you move it in, you will get an extra term here, right? And so if you want to put this dB dot G dt, you will get two terms. Okay, this term plus a dB dt term, okay, dot G. So this is differential by part. It's like any two things, A times B. If you want to take the time derivative, you will get two terms from it, dA dt times B plus A times dB dt. So it's also the same for matrix or vectors. If whatever A is scalar or matrix or vector, as long as you can multiply these two, it's always, you can do differentiate by part, right? So similarly here, you do differentiate by part. So therefore, you cannot just simply move B into this thing, because these two terms are not equal to each other for nonlinear problems or time-dependent Jacobian. So then what can we do? In ILDM, the treatment here, if you assume, if you read the ILDM paper, it says, we just assume the reaction rate along the direction for the eigenvector, this particular eigenvector, it vanishes, it disappears. So what it means is if you do the projection of the left-hand side and the right-hand side, both to the eigenvector, so you just assume the right-hand side equal to 0, regardless of what happens to the left-hand side. Why the left-hand side can be 0, I will talk a little bit more shortly, okay? But this is obviously, this assumption is not the same as the linear algebra, because this guy is not a dfdt, and f doesn't go exponential decay to 0. So most cases, you find the mode, this mode here, this mode here, it doesn't decay to 0, but it goes to some kind of finite number for nonlinear problems. So it's really more difficult to deal with, right? So for real life chemistry. So by the way, if any of you have questions, feel free to ask, because this can, so somehow this procedure can be very confusing for whatever reasons. So different people get stuck at different places. So if you get any question, just feel free to ask, and we can clarify it, so you don't have to get stuck over the entire slides. Now, so after LDM, so there's the third method called the CSP. CSP is a method. The formulation is quite similar to the previous two. And if you look at the same equation, okay, you look at the left-hand side. So basically, you get a B dot dg dt on the left-hand side. The right-hand side is B dot G dot G. Okay, the left-hand side, since you cannot move it in, so why don't we just split it into two terms? One term is you move it in, and then you spit out the other term. It's from differentiated by part, right? Like what we did. So basically, this one B dot G is called F again, because F is equal to B dot G. So we get a term which is dfdt, just like what we did in the linear case. But there is an annoying additional term here, which is involves the eigenvector dt dot the source term, okay, the reaction rate. This term obviously is not 0, as we argued in the ILDM case. So in ILDM, you assume this term is 0. So ILDM assumes this term is 0. The difference between CSP and ILDM is CSP actually assumes this term is 0. They're assuming different terms to be 0. If you assume this to be 0, what will happen is this term you have to keep it. Okay, if you don't ignore this term, you have to keep it, and you can move it to the right hand side. Yeah, if you move to the right hand side, you can combine this term with the original right hand side, and the left hand side you just ignore it, set it to be 0. If you compare this one, so there's dBdt here, right? There's B dot G here, and there's a common term G. So you can lump this term together with this guy to get a dBdt plus B dot G. So in linear algebra, if B is eigenvector, B dot J is lambda times B. Okay, lambda B. But then we have dBdt term plus this. It's getting more complicated. And this term, after being lumped, actually in CSP, we call it this B0. It's called a refined vector, or it's called CSP vector. So B0 is defined to be the original term plus the remaining guy from the differentiated by part. So this additional term, if you lump it together, what is claimed by CSP is this B0 is pure, it's more pure vector or CSP vector, which can give you a better quality or high order accuracy in the algebraic equation. So in other words, if you approximate this guy to be 0, if you here, right, you approximate df/dt equals to 0, you equivalently approximating this guy b0 dot g equals 0. So the major difference or major argument between CSP and ILDM, unfortunately, this has never been very carefully discussed in the literature. If you read papers, it's never been even seriously discussed. What's really the difference? How whether it's the CSP approximation approximating this guy equal to 0, is it much better than approximating this equal to 0? It was claimed in CSP literature that this approximation is better, is of higher order accuracy. Okay, this is leading order accuracy, of course. So our job for model reduction is we need to figure out whether this is the case, whether this claim is true or actually there are some issues in it. Okay, so we need to look at it. So, but if you read CSP literature, actually the major difficulty to understand this part is about the notation. And the refinement for CSP, if you find it, it doesn't write simply like this. It has this subnodes, the subscript. Basically, it do the IGs, many sigmas. When you look at the sigmas, you get lost to what it actually means. So it's a lot easier to look at this matrix vector notation like this one. So I translated this notation to something easier to understand. So you look at this notation, it can help you much better understand what two different methods are doing here. Okay, and if you want to refine a whole bunch of vectors altogether, this is what provided by the CSP literature. Okay, so it's called a CSP refinement. The CSP refinement is really the essence or the heart of the CSP procedure. And it was claimed to be a asymptotic process. Every refinement, the accuracy should be increased by another order. So let's see whether this is the case. So now, if you want to compare the different methods, we just put the errors from the approximations or assumptions, put them together. Well, let's compare them one by one. Okay. Remember, if you get a df/dt equal to lambda, or what happened to this pain? B dot g, okay? Lambda b dot g dot g, okay? If you have this equation and you want to approximate this equal to b0, the error induced was from left side. So the term you ignore, okay? The right hand side basically is lambda times b times g. It's similar for every three terms. The right hand side, after you do the propagation, it's all almost in the same format. So basically, you don't get errors from right hand side. All the errors from the approximation was from the left hand side. So what you do is you compare what kind of error it induced by your approximation. For linear system, of course, it was from here. For example, if you get df dt is equal to lambda times b dot j, right? If you approximate this equal to 0, you can divide lambda to here. So this one will give you the source for error. So it's here. And because, so basically f0 e lambda t over lambda, that's the really how much error you have here, okay? And the ILDM, remember, it was b dot this guy. You don't move it in, so you just keep everything together. So this is error for ILDM. And if you compare ILDM with eigenvalue decomposition, so there are two things you want to pay attention. One is lambda. Why do we need to specify or choose a large lambda? Okay, lambda have to be large in magnitude. For example, it must be 100 times larger or 1,000 times larger than the timescale for the controlling processes, because we want lambda to be large to get a smaller error. Okay, laminar go to the bottom. If you get a huge laminar, you get a small approximation error, right? That's one thing. That's why we prefer to use large laminar. If your laminar is small, your error will be naturally large. Does it make sense? Yeah. And for linear system, you get another benefit from the top. So when laminar is large negative, it decays to zero exponentially. So the linear system really have two processes all together, making the error extremely small. So for linear system, if you get a large lambda, your error is almost negligible in most cases. So QSSA approximation for linear system is probably the best approximation you can find ever. Okay, I studied math for many systems, but the QSSA for fast, like a decaying mode for linear system is almost perfect. You in many cases you can almost treat it as exact. Okay, for model reduction, if you can get a approximate linear system and large negative eigenvalues, your error, you just cannot see that. Right? In most cases, I will show you. The QSS approximation is fantastic. If you apply it correctly, your error is almost always negligible. Okay, but for nonlinear systems, the story is a little bit more complicated. On the top, if you look at the top part, it doesn't go to zero. It stops at some kind of because like for nonlinear case, it doesn't go to zero. It decays to some kind of finite amplitude and then stop decaying. It's that's typical nonlinear process. Okay, because DG and B, they may have some kind of funny business with each other, so they don't decay to zero. And then the only thing will guarantee you to have small error will be large lambda. So that's the case. If you don't have a large lambda, you are screwed there with your. So large lambda is only guarantee for you to control the error for this ILDM process. Okay, but in most cases, if you think the error is still very good. Why? Because if you think what kind of lambda we have for real chemistry, the controlling processes, like the ignition process and the rate controlling things, are measured in microsecond or millisecond, as we said, right? If you have a combustion system, you need to deal with like a millisecond, 10 millisecond, or even 100 millisecond. That's the rate controlling process you need to resolve. But what is the radical timescale? As we said, radicals has, if it reacts with any major species, it has an extremely short timescale because it doesn't have, almost has zero activation energy. So a radical collide with a major species, it will react. Okay, so that means its timescale is almost collision timescale, or in some cases you get a slightly non-zero activation energy, but a few collisions is fine. So typical radical timescale will be sub-microsecond, see nanosecond, 10 nanosecond. So that's typical, okay, or 100 nanosecond. So it's typically 100 times or 1,000 times shorter than the rate controlling processes. And if you think you get a 1% error in your approximation, what's the big deal, right? And your uncertainty in detailed chemistry will be 10% in best case, as we argued. So therefore, QSSA, if you really choose a good, again, a good candidate for the approximation, the accuracy is really good. But things will get worse if you become very aggressive. Okay, if you want to be aggressive, let's see, I want to include more species in the steady state approximation, then you need to relax your criteria to choose some kind of not that big lambda, or to include radicals or intermediate species not that fast in your approximation. If that's the case, you will see from 1% error, it becomes 10% error, or become 5%, like 1 or 5, 20%, 30% error. When your error go to 30%, you start to find surprises start happening. It's not always bad. Sometimes you can find it still working, but the chance for having surprises increase dramatically. You find if you're being aggressive, your customer will keep on calling you every once in a while to call you, oh, what happened to this approximation and why it fails? It doesn't always fail. The frequency of failure increase dramatically if you are becoming more aggressive with the threshold. So in this sense, when we deal with timescale-based reduction, we want to be very conservative. For example, we want to use 1% error as a threshold, or even 0.1% error as threshold. And the good news is that if you are aggressive or non-aggressive, actually, you can really add a lot of more radical to your approximation. So for example, if you use 1% error, you get a 20 radicals as called a steady state. Okay, but if you tighten up your threshold by a factor of 10, you probably get another 4 or 5. Not a big deal. Okay, not a big deal. So in my experience, to be more aggressive, to be very aggressive in specifying timescale threshold, doesn't pay off. Okay, we want to be safe, because if timescale approximation fails, you can be miserable. You can get a totally wrong result, because your equation from algebraic equation, it can give you all kind of surprises. It can crash your programs sometime, or give you totally wrong solutions by orders of magnitude. You definitely don't want that happen. So this kind of errors typically you don't see in scalar reduction. So for example, you throw away some species, typically it's very difficult to mess up the mechanism, give you factor of 10 error, right? But if you mess up time scale reduction, if you are too aggressive, you can mess up the solution by factor of 10 or factor of 100, sometimes even by many orders of magnitude. So it's very scary stuff. I guess, so, but if you apply this conservatively, you find the accuracy is fantastic, okay, very, very well. Now, the story here is when we look at the CSP. So CSP, the error source was from left-hand side also. It has 2 terms, okay? But if you want to see the claim in CSP, it says the error is asymptotically smaller than that of ILDM, or the linear approximation. What happens is the top part, the 2 terms together here, these 2 terms is dfdt, okay? We put together equal to dfdt. If you assume this guy is equal to 0, your error has 2 terms. How can you make this term much smaller than this guy? This term must be much smaller than this. Okay, let me wipe this off so you can see it more clearly. So what you can see, this term is this term, okay? If you want to make the summation for these 2 guys much smaller than this one, the only possibility, you have to make these 2 terms cancel. They must cancel each other. That's the only possibility you get a much smaller error, right? Okay, so the only possibility where CSP can give you higher order accuracy is b dot dg dt must be approximately equal to negative db dt dot g. And you get the vectors here, okay? So sometimes this is true, okay? In CSP literature, you can find sometimes you can find toy problems. People don't have a lot of toy problems. Actually, a few papers in the CSP literature can give you some toy problem, and those toy problems are carefully constructed to make sure these 2 are balanced, and then indeed you get a better accuracy from the CSP vector, okay, the approximation from CSP. But in general case, if you think there are two things. If B is eigenvector, how is it defined? It's B dot G equal to lambda B, right? So this is the only equation eigenvector need to satisfy. It doesn't have to satisfy this equation. So therefore, for real life problems, eigenvector doesn't satisfy this equation. These 2 terms are not equal to each other. It just doesn't happen. So if you read the CSP literature, you find for real life problem, we always use eigenvectors, and almost all this work, just ignore this term. Just ignore this term as is, because if you included it, it's not a 0 either way. But if you ignore it, you find this CSP procedure just reduced to ILDM. They become identical, okay? And that's the funny part of it. So if you check this, it's kind of a really awkward situation, because this complicated math doesn't pay off, okay? There are 2 things that doesn't pay off. First of all, if you want to achieve the higher order accuracy from CSP, you need to solve this thing. You cannot use eigenvectors. So you cannot use eigenvectors, and there's no actual other vectors found we can use easily for real chemistry. And you have to construct your own vector. You cannot use eigenvector. You need to choose your own B vector and its derivative. So that means you need to design or engineer a vector as a function of time, which can give you better approximation of this. So this B0 need to be engineered or need to be solved. But if you really want to solve it, you will find you need to solve for a much larger system. Like this equation, you need to solve together with the original ODE. Okay, you can possibly find you can find a combination of B and dBdt, which indeed let these two terms cancel. But you need to solve this additional n equation together with the original ODEs. So you are solving a much larger system. You no longer get a model reduction. It's not a reduction anymore. Actually, the system becomes much larger to solve. And together, there are other more complicated issues. So, so this tells us actually for a lot of cases, if you want to get a very complex or advanced mathematical theories, try to help you to do better. There's a price to pay. Okay, you want higher order accuracy. First thing you want to think is whether you need the high order accuracy. The second is how can you achieve it? Whether your design method it can give you the thing you want or not. So first of all, for model reduction, it's really hard to argue we need to achieve a high order accuracy, because if you think if we get a 10% error for combustion problems, ignition delay time, flame speed, whatever, we are pretty happy, right? So reduced model, if we want to get 10% error, that's pretty good. But if you get a high order accuracy, we want our reduced model to be like a 1% error or 0.1% error. We're beating ourselves too harsh, right? Too harshly. Basically, we probably never found a real application. We do need a high order accuracy. So for this reason, you will find in the literature, actually, we never use CSP to really reduce the chemistry to achieve high order accuracy. So that's something I guess we need to learn. So probably the lean first order approximation for LDM is good enough. Okay, it's good enough. So if we want to use it, there's another thing coming out. Even though we don't want a second order accuracy, and we just want to use eigenvector, eigenvalue, it's not cheap to perform eigen decomposition. So let me show this here. For eigen decomposition, if you want to do question posted, let me see. I'm confused why BG or B dot 0 can simply be set to 0. In general, for LDM CSP, it makes sense to me. Oh, that's a good question. I guess you gotta. Let me explain a little bit more. Okay, you get dGdt is G time G, right? So you do B dot this one and B dot this one. This one give you laminar times B times G. So we can approximate, we can assume like after normalization, like a proper normalization, G and B are all normal numbers, but laminar can be a large guy. For example, it can be 10 to the 4, 5 order, a large guy. If you move this laminar to the other side, you get a B dot G equal to 1 over lambda, whatever you put here. Okay, this is order 1 term. You will see this term, because 1 over lambda, this term is, you can call this order epsilon. Okay, epsilon is 1 over lambda. So epsilon defined to be 1 over lambda. And this is a small term compared with the other terms for the dot product, because B dot G is dot product. You have B1, G1, B2, G2, B3, G3. And all the other terms are order 1. And the right hand side, this guy is order epsilon. If you ignore the order epsilon, you can still relate the other species with quite good accuracy. Okay, the accuracy will be order epsilon. That's roughly the error. I hopefully this answers your question. Okay, in this sense, so once you have a large number involved, so that's pretty much what you can do, play with the asymptotic analysis. When you identify a small or large number, you can just throw away whatever terms multiplied by the small number, and only keep those terms without this small number. Okay, so that'll give you a reduced system to solve. All right. Okay, so where am I? Okay, so if you want to use ILDM, the simpler approximation, just to approximate this guy equal to 0. If you just want to approximate this guy equal to 0, what will happen is you just need to do eigendecomposition, right? So if you have Jacobian, you can call MATLAB or whatever LAPACK functions to compute its right eigenvector, and then to inverse it to compute the left eigenvectors. So basically do a eigendecomposition. If you have n variables, what cost, the computational cost for eigendecomposition is proportional to n to the cube. Okay, and the inversion for the matrix also is function of n to the cube. So when you have a lot of variables involved, a lot of species involved, when you get a large mechanism, you do eigendecomposition is very time consuming. You will find actually it's more time consuming than just solve the governing equation directly. Because for most good solvers, so decent solvers, the computational cost typically is order of n squared. Someone can even achieve linear cost. Okay, so to computational resolve a full system, it typically functions n squared or n in the best case. But to do eigendecomposition, you give us a cubic function. It can be a lot more time consuming than just solve the original system directly. And due to this reason, you will find that nobody actually do eigendecomposition at real time when you want to simplify a solver. It just doesn't pay off. It give you actually making it more difficult to solve. Okay, that's what happened. And therefore, if you really want to apply this timescale based reduction, particularly based on the eigensystem, you have to really think of a way which can reduce computational cost. How can you reduce computational cost? Because otherwise you cannot really use it in real simulations. Okay, I was just skip this one. Now this whole slide is one big deal for CSP. So basically it tells us second order accuracy. If you want to achieve it, they're unfinished business yet. Okay, I guess if some of you get interested, you can dig into this to figure out whether you can design or develop a new formulation rather than the current CSP theories to use eigenvector as starting point. To start from something different, we need to find different initial set and like B and dBdt. If you can find it, you can probably achieve high order terms. Actually, so Professor Lam basically has been advising me for quite a long time, over 10 years. And he taught me math, fluid, and CSP theory. So he was in my committee studying this CSP reduction. So I learned a lot of things I can think of from him. But one thing he just didn't finish in the end is still how to find vector B, which can give you this high order. So he was trying all different things in the end. For example, from the fast reactions, using the stoichiometric coefficient. If you read his recent paper 2 years ago, so he was trying to use some reaction rate direction, based on stoichiometric coefficients. But there are all different sorts of issues, very complicated. So far, the issues still remain unsolved. Okay, so if you're interested, that's a very interesting math stuff to dig into. So you can use this to hone your skill, I guess. You can learn a lot of interesting stuff. But to really use it, I guess, first of all, probably it's hard to find a case really you need the high order accuracy. And secondly, you do need to complete the system, to close the system. So you can find a viable vector to start the CSP refinement actually. Okay. Now, so how can we really use timescale based reduction in real simulations? The interesting story is if you look from almost 100 years ago, in the early 1900s, actually, people developed a method called a steady state approximation for species. We call it canonical called the steady state approximation, which is different from the one based on eigen decomposition theory. Okay, so what this says can be illustrated by this very simple example. So if, for example, if you get 3 species A form some radical B is radical, I plotted in red color, you know it's radical. And once these radicals form, and they can quickly collide with something else to become product C. So this is almost like a bucket of water. B is like a bucket, okay? You get a slow input, but you get a big hole. Whatever comes in goes out. So your concentration of B cannot actually accumulate in the system. Due to this reason, if you get this kind of scenario, big bucket with big hole on the bottom, you can always approximate the water level inside the bucket is approximately equal to 0, right? And this is called the steady approximation. So that says whatever comes in, it just goes out. So basically, the Q out, it balancing Q in, or the consumption rate for B balances formation rate. If you want to write down the mathematical equation for this one, it's rather simple. You write down dB dt is how fast the concentration of B changes with time. You call it to the formation rate, which is 1 times A. 1 is K, so basically K is equal to 1 for this case, time concentration for the reactant. So 1 times A is the formation rate, right? How fast B is formed. And then consumption rate is 1 over epsilon. This K is equal to 1 over epsilon. So therefore it's 1 over epsilon times B here. And this one should be equal to 0 if you approximate B doesn't change with time. Okay, dB dt time equals to 0. It tells you the accretion rate must be, the formation rate must be balanced by the consumption rate. So that's the physical essence for this steady approximation. And solving this equation is super easy. You know, it's B is equal to A times epsilon. And pay attention to this little epsilon here. Okay, epsilon is a small number. That means if you get a small epsilon or fast consumption reaction, B's concentration has to stay low. And this is perfectly consistent with our intuition, right? It makes a lot of sense. And this called a steady approximation actually has been used over many decades. And it turned out to be very, very useful. And it's quite easy to use because look at that. This equation is rather easy to solve, right? Much easier than solving eigenvector, eigenvalue systems. So much easier. But if we get a large system, how can we just systematically identify all this called steady state species and make sure? So by the way, this classical QSSA actually doesn't conflict or contradict to the eigen decomposition. So for example, here if you see B minus A epsilon equal to 0, if you approximate this one, you can construct B to be 1 minus epsilon, right? Let me see. Yeah, times B. Let me see. Oh no, A. Yeah. So sorry. A. Why it doesn't write here? B over epsilon. So 1 over epsilon to A and B. My goodness, this is difficult. Okay, this is approximately equal to 0. And what if you just call this B? Okay, this B vector to be 1 over epsilon. It is eigenvector. It's actually indeed an eigenvector. If you look at the Jacobian, like if you write down the ODE for this linear system, it's dABC equal to the Jacobian. The Jacobian is here. Okay, you can easily write it down. And you do eigen decomposition, you find indeed. Okay, so basically B is a small term with 1 times lambda 2. Okay, so you get epsilon 1. Okay, so a small term here, large term here. So basically, when you dot B with A and B, so it tells you this guy has nobody to fight him. Okay, so that's why he has to decay and disappear to balance the small term. So if you look at the eigenvectors, if your eigenvector only have one large number, everything else is small, so that can give you a QSSA species, right? So if you find an eigenvector with large negative eigenvalues, and you look at those entries in the eigenvector, one eigenvector is only one entry is big and everything else is small, that'll give you indication for a good called a steady state species. Actually, it makes a lot of sense, and the math is super easy actually. Okay, but one thing to be careful is for real system, you need to get rid of those inhomogeneous variables from the B vector. Okay, if you get an ODE, typically you get a temperature, speed, concentration involved. If you have other quantity other than concentration involved, your B, different entries in B can have different units or different dimension even. So you really cannot compare the entries with the same with different dimensions. So therefore, the trick is that you treat temperature to be fixed, a given. So you simplify your governing equation only for speed and concentration. So therefore, you can compare the different entries for B. Okay, in that case, then the comparison makes sense. This is a very, very important thing to keep in mind. Never compare entries with different dimensions. So for example, if from the previous thing, if you get a vector B like this, a lot of people get this B from the original ODE with temperature or sometimes even velocity or pressure involved, the flow property involved, and you get this B, you find you want to find some dominant entry there. So how do you find dominant entry? So people say B dot B, right? Dot product or A dot A. So frequently we want to look at the dominant entries, and we want to normalize everything to be positive. How do you make it positive? B dot B, right? So first of all, this dot product should never be done. Okay, so because if you have different entries have different dimensions, how do you do the dot product? Okay, so for example, if B has temperature and Y, and dot product T times Y, so how do you dot product these two things? You get a T squared plus Y squared. You cannot sum them up. Okay, so any vectors with dimensions, which is at least not a dimensional homogeneous, you just cannot do the dot product. And we get actually published papers in the society dotting product the B vectors. So that's a serious issue. Okay, so just never do this. Keep in mind. All right. So, but this one tells us it's kind of a very simple way we can look at an eigenvector to see whether you have a unique entry in this eigenvector to indicate there is a good quasi-steady state species. And the thing is, in a lot of cases, you will find many eigenvectors actually only have one large entry. So that makes your life a lot easier. So you can easily pick this guy to be quasi-steady state, and then you can assume it's quasi-steady state. Never need to bother do eigen decomposition on the fly. So this helps us to pick which species is in quasi-steady state. Okay, let me see. We get another answer. Once timescale-based reduction is done, can the equations be solved explicitly or implicitly are still needed due to the stiffness? So timescale-based reduction, we can remove the fast processes. Okay, but typically, if you do time integration, your time scale it's still longer than some of the remaining fast processes, because some of the marginally fast radicals you shouldn't approximate to be called a steady state. Okay, or there are some species it's fast here but slow in other places. In that case, you cannot approximate this guy to be called a steady state everywhere because it's bad somewhere else. So give you an example. If you get a 1D premixed flame, so some guy, a radical is fast in the flame zone, in the reaction zone, where temperature is high. But in the preheat zone, temperature is low. You find actually it's becoming slow. The same species can be slow on the low temperatures. In that case, it's bad called a steady state species at the preheat zone. So you shouldn't approximate to be QSS everywhere. Then you have to leave the species in the ODE. In that case, after the time scale reduction, you get this marginally fast species retained, okay? And you get this kind of some more fast, some more slow species retained. These guys can give you stiffness, okay? So therefore, after time scale based reduction, the system typically, they are still stiff. And you still have to use stiffness based solver. So reduced model applications, it's kind of tricky business. It's always give us troubles. Okay, we that make our life more interesting, I guess. The second question, in diesel combustion simulation, should high temperature mechanism be used, or merge the mechanism of low and high temperature be used? For diesel application, diesel is compression ignition application, okay? Because you compress air first, and then you discharge the fuel to the chamber, and then auto ignite. You don't have a spark plug to induce a flame in the beginning. So you do need to wait for radical pull to build up. So ignition delay time will be important. And the temperature range for diesel application, it ranges from 850K, 800K to 900 something K. For some cases, if you be very aggressive in compression, you can go to about 1000 Kelvin. If it's always above 1000 Kelvin, you probably can get away with using high temperature chemistry only. But if you have 850, 900 Kelvin, 950 Kelvin, you do need to include low temperature chemistry. Okay, the rule of thumb typically is if you have initial temperature above 1200 Kelvin, 1200 Kelvin is quite a safe cutting line to throw away the low temperature chemistry part. But if you have anything below it, even 1000 is borderline. 1100 Kelvin is a borderline too. You can still see some kind of effect. Anything below 1200 Kelvin, it's just better to keep low temperature chemistry. Okay. If someone is not picky, it's another story. So, all right. Okay, so it seems the QSSA can be a very easy thing to use. Okay, it's a very easy approximation to use. I actually have been using probably the #1 widely used approximation in the broad society. Everybody is using QSSA because it's simple, fast, and accurate. But there's one thing here is if we look at another thing. In chemistry, there's always surprises. One of the surprises here is another canonical approximation called partial equilibrium approximation. What partial equilibrium is if you have a reaction which is fast going forward and fast also going backward. So whatever goes this way can quickly come back. Okay, and then B and C quickly reaches kind of partial equilibrium or approximately equilibrium state. In this case, people approximate like the concentration, like for example, omega 2 approximately equal to 0. So that means the forward reaction rate balances the reverse reaction rate for this reaction approximately. Okay, this reaction rate, basically forward reaction rate, is B times 1 over epsilon. Okay, for this K forward and K forward, K reverse is both 1 epsilon, just to make our life easier. Okay, they're both fast. So forward reaction rate is K times B. Okay, so it's 1 over epsilon times B. The reverse reaction rate is C over epsilon. Okay, so they must roughly balance each other. In that case, you get B approximately equal to C. Or in other words, B and C, if you look at this kind of connected containers, if you get a strong connection between part B and part C, their water level always stays some kind of related, right? This is called partial equilibrium. For partial equilibrium, a lot of cases people say partial equilibrium is easy to apply, right? But actually it's not. Why? Because first of all, if you look at this equation, B just need to be equal to C, okay? But it doesn't have to be in low concentrations. Just like for these two containers, you may have very little water in it, but you can have a lot of water. So the concentration for B and C are arbitrary. So they may be in high concentrations. If they are in concentrations you just cannot always approximate this one because they can have a lot of business to do with transport term. If you solve B and C using this single equation, you are ignoring all their mixing term, all the transport term. So the convective term and diffusion term are all ignored. And you know, for some cases, if you get a high concentration and you ignore the transport, you will get a big trouble, right? So that obviously, clearly, equilibrium approximation is more difficult to use for the steady state species approximation. Although they are both canonical, you find the QSSA for species is used everywhere by almost everybody. Okay, the partial equilibrium approximation somehow only appears in textbooks. So people construct textbook toy problems to demonstrate this wonderful idea. But you will rarely, almost never see any people actually using it. And this is a major reason because this equation is algebraic equation, but it's very difficult to use. You just shouldn't approximate this in a real flow because B can have high concentrations. Okay, another thing, the difficulty in resulting from mathematics is if you look at this model, okay, you can also write down in the linear format, basically the dj dt equals g times the variables. And if you do the eigendecomposition, you find your vector here is associated with large negative eigenvalue. Okay, so this is B, basically B times your G roughly equals to 0. So it tells you ABC. Okay, so this one times ABC, what do you think you get? This is tiny small term. This is order 1, this is order 1. This equation tells you B and C are fast guys. Okay, it tells you 1 times B minus 1 times C plus some of the order of the epsilon must be equal to 0, approximately equal to 0. So you can ignore this term, and this gives you the canonical partial equilibrium. So eigendecomposition is give you the same story as the canonical PEA or canonical. So the thing is, if you look at this difference here, this equation tells you 2 fast guys. Okay? If you think in the QSS case, it gives you 1. What's the difference? The difference is that if in QSSA, if you have this case, a single large number, it can determine the concentration for the guy, okay? So you can solve this equation to find what B is equal to. It's a small number, but you can solve for what B is equal to from this equation. But what happens for this one? Can you solve this for B, what B is equal to? No, because you get 2 unknown variables, both B and C. You can solve the relationship between B and C, but you cannot solve what B is equal to. It depends on what C is equal to. So B is equal to C plus some order epsilon. You don't know what C is. So basically, this partial equilibrium system, the essence is it gives you an algebraic equation, which is not enough to solve for the fast variables. But the QSS system, it can give you a unique answer. So you can solve for a concentration for a species using the quasi-steady state approximation. But for partial equilibrium, you find you don't have enough number of equations to solve all the fast variables. Okay, so that's a mathematical reason why actually you cannot easily use PEA. You just don't have enough number of equations for it. And if you want to apply the PEA, you have to do some manual derivation, somehow to formulate it, to blend those algebraic equation into the ODEs. Okay, so basically, if you get 2 fast variables, okay, you get a 1 equation for PEA. Okay, so you have to, you cannot solve for 2 fast ones. So somehow you can blend this one together with the remaining ODE. You can get rid of 1 ODE from the system, solve the remaining n-1 equation together with a single fast variable. And it makes your life absolutely miserable because you need to do a lot of derivations, a lot of manipulation in the equation. So your governing equation and your computer code need to be rewritten to use partial equilibrium reactions. That's why almost never anybody wants to use it. Okay, so that's I'm trying to explain what happens to before. So here we put together this comparison of these two different methods, QSS versus PEA. Just keep in mind, QSS species always in low concentrations, okay? But fast reactions involving partial equilibrium, the concentration can be arbitrary. So because concentration can be arbitrary, you can't really ignore their mixing terms. Very annoying, okay? And furthermore, if you have a QSS species, because its concentration is always low, it doesn't have it here, it doesn't have it here, their diffusion term is almost always not important. So you can check their transport term, mixing term for the really good QSS species. You find they're almost zero everywhere. So they don't have exchange from different locations. So in that case, their mixing term, transport term almost just can be ignored from the governing equation. And the resulting equation is only involving chemical reactions. Okay, you can solve a very simple chemical reaction balancing to solve for a QSS species concentration together with other species. So as a result, QSS species can be hidden or can be removed from a transport equation. So that's a big deal. You indeed, instead of solving 100 transport equations, so each equation for each species, probably you just need to solve half, like 50 transport equations. And the remaining equations are algebraic. The algebraic equation, you can probably have ways to solve them very efficiently, use eternal iterations or use some kind of whatever advanced solver method. You can indeed solve those hidden part of the QSSA very efficiently. So as a result, using QSSA can save you time, can save you a lot of computational time, and it doesn't give you much error. The accuracy is perfect in most cases. Okay, so therefore, timescale-based analysis, but timescale-based reduction. So when we talk about it, we get all different wonderful theories. Keep in mind, a more complicated theory doesn't necessarily always help you. Okay, although some of the concepts in this series, many cases are helpful. If you really want to get a serious reduced model based on timescale analysis, so in a lot of cases we find the canonical QSSA probably the only option, which is easy to use and with very good accuracy actually. Okay, so in this sense, so timescale based reduction has a lot of issues, which I think is not adequately discussed in the literature. So it's causing a lot of misunderstanding. I think it's a lot of people think more complicated theories can be easier to understand. Not the case for model reduction. Okay? For model reduction, if you can use simple tools, try simple tools. If simple tools is enough, you probably just don't bother to beat yourself, to make it too complicated. Okay? Making it too complicated has, as I said, it has side effects. First of all, people just won't be able to understand what you're doing here, and say nobody wants to use your method. So I have a previous experience. I have a very simple like DRG method, which to my surprise, a lot of people are willing to use it because it's simple. It's very, very simple. Okay? But I have a more advanced tool for QSSA using a lot of wonderful computational theory. I will show you next. Okay? Just try to impress you. But very few people want to use it. To my surprise, I always think my work on QSSA identification and the solution for QSSA equation is probably the masterpiece for me. Okay, if you're interested, you can go dig into it. But very few people want to use it. Very few people want to use it. So yeah, can you please repeat what QSS species can be removed from transport? Or why QSS species can be removed from transport terms? Yeah. Let me explain a little bit more. Why QSS species can be removed from transport terms? Okay, because if you think d, y, dt, if you transport equation, so the convection term is here. So basically, it's omega y. So how fast y is formed from chemical source term plus diffusion term. Okay, diffusion term typically, what controls diffusion term? Of course, the gradient. Okay? If you have a field, suppose you look at a y. You get a large gradient here. So basically, you get a large flux, diffusion flux. So when you get a large flux, you have to carry this when you solve it. For QSS species, If you look at the concentration, this is almost zero everywhere. It's just almost zero everywhere. So therefore, you look at the gradient y, if it's QSS, it's typically much smaller compared to its production rate and formation rate. So QSS is primarily formed from chemical collisions. Like, so some molecule collide to give you a radical, and the radical is consumed in place. Okay, with very few exceptions. For example, H radical is not a good QSS. That's why its concentration can accumulate. So H probably is one of the slowest radical. So its concentration can come up, and that's why it's so important, because it's a high concentration. It plays a very important role. The other radicals serve as an intermediate stage. People comes here and just go. They don't accumulate, so it just serves as a connection point for different reaction pathways. So therefore, if you look at a really good QSS species, you take the gradient, it's almost never important. So therefore, you just can throw this away. And this term, by definition, is approximately equal to zero. Okay, so if you track its concentration, how the radical concentration changes with time, so you are approximating the radical is formed locally and consumed locally. Okay, that's a very accurate approximation for most cases. Hopefully this answers your question. Okay, and this is very simple fact. Actually, it's the reason why this 100-year QSSA has been used everywhere, everybody. It's really a working stuff. It's like a screwdriver you can use. So we don't have many handy tools we can use in model reduction. A lot of tools actually not that rigorous in terms of math. But QSSA is quite rigorous theory in math. And it's quite simple. It's very useful, very useful. So if you are interested, definitely dig into this, okay? But the thing is, if you get 1,000 species, or even after reduction, you get 200 species, and how do you find which species is QSS? Because if you look at this B vector, you find when B vector becomes very long, you find this guy is one here. But sometimes there's another fast vector. Okay, it's fast here. So if you get two fast species, for example, A and B, okay, and you get two equations, actually you can still solve it. So it's not always like if you get a multiple large entries in a long vector, it's always a bad case. So there's a possibility that you can find B vectors with multiple large entries. But if you group them, you find you can still uniquely solve for the concentration for the fast ones. As long as the equation is solvable, then you get a complete set of equations. But if you find your equation number is not enough, but that means you get some partial equilibrium stuff inside. So in reality, there's almost always some kind of bad guys, which is fast, which it looks like a radical, and it involves partial equilibrium. But how do you exclude those guys from the system? How do you find those bad guys and only to keep this good approximation for QSS? Actually, so what we did here is many years ago, I come up with this theory based on projection. So the projection matrix, which is part of I learned from Harvey Lam when I work on CSP theory. So I tend to call everything CSP. But this projection basically is also a concept in linear algebra. Okay, if you want to, if you have an eigenvector, okay, if we have an eigenvector B and a column vector, so this right eigenvector and left eigenvector, you call this multiplication for this column with the row to be matrix. This gives you a matrix, right? This matrix is called Q matrix. You probably heard about this Q matrix. So if you get an n by n matrix, you get n projection matrix. We call it QI. Okay, and each projection matrix actually it gives you a lot of information. Okay, because you get many entries in the Q and diagonal elements in this matrix. It basically tells you which species is responsible for this mode. If you find this guy is 1, everybody else 0, that means this guy is a guy who give you the fast mode. But if you find 2 large entries, it's the interaction between these 2 guys give you this fast mode. Okay? Using this projection matrix, actually you combine all the fast modes and the slow mode. You can for any identity matrix you can decompose into Q fast plus Q slow. Okay, so one projection matrix is telling you who is responsible to the slow group, and then another one tell you who is responsible to the fast group. So you divide all the modes into fast mode and slow mode. People call it fast-slow separation. You can do the fast-slow separation with eigen decomposition, with ILDM, or with CSP, whichever you like. But you can separate the fast thing with slow thing by setting a threshold, right? Which is the cutting time scale. Faster than this, you call it fast mode. Slower than this is slow mode. And then you combine all the projection mode for the fast guys. That's called the fast projection matrix. You combine all the slow ones, it tells you all the slow projection matrix. So physically, it just tells you who is responsible to the fast group, who is responsible to the slow group. Okay. For the QSSA, so one simple thing you can derive is basically if you find some guys only appears. Like if you look at the entries, the diagonal entries in the Q slow, for example, if you find somebody is 0 here, okay, if you find a fast species has no business with slow space, with slow mode, that means everything it does is in fast mode. Okay, so it can be fast by itself, or it can be interacting with somebody else to be fast as a group. But all its information can be determined only by just by the fast mode. In that case, that it must be a QSSA species, because any fast species involving like a partial equilibrium, their difference, if you look back this here, okay, the difference between B and C is always small, right? But the sigma of, so if you B plus C, it's always a slow mode. So the partial equilibrium, each partial equilibrium will give you fast mode, which is B minus C, and a slow mode, which is B plus C. So that is the conservation for B and C together. If you get a tank of water, if you count the 2 tanks together, the total amount of water is conserved, right? So therefore, this is slow mode, this is fast mode. So the lesson here is, so if you find a fast species, okay, fast species, how do you know it's fast species? You look at the Jacobian diagonal entry, they call it lifetime. So if you get a large diagonal entry, that is fast species. That means the time scale is short. And if the fast species has anything to do with the slow space, it must involve some partial equilibrium reactions. So you cannot assume that to be called a steady state. If you do it, you will find your error will explode in some cases. So that's a very simple strategy. Or, well, this method is what I developed many years ago. Okay? It looks like a fancy. I guess I explained to you guys how this works. You still don't understand what but there's another way to explain it more easily. So if you want to understand what happens, you put all the large entries. You look at the Jacobian. Okay, let me explain. You look at the Jacobian. You find all the large entries. Small entries you ignore. So if you find large entries, you form a subsystem only consisting of large entries, and you find if you can solve it. If you can solve it, you can use this as a QSSA. That's much easier way to understand. It's that simple, okay? It's like you find the large entries because everybody else is small. So you pick the large entries and then you form a subsystem. If you can solve it, that's a valid set of QSSA. So I guess this way everybody can understand it, okay? If you cannot solve it, that means you don't have enough number of equations for example, here you can involve 3 fast species because you get 3 rows for 3 rows large entries, right? Large numbers. And oh no, 1 column each column is one variable. You get a 1, 2, 3 fast variables. You get three rows, 1 row, 2 row, 3 row. So 3 equations for 3 fast variables, you can solve it. But some cases, if you find your scenario be like this, 3 entries here, 2 large entries here. Now you get a 1 fast variable, 2 fast variable, 3 fast variable, but you only get 2 equations to use. This case you cannot solve it. Then you just cannot assume the 3 guys are QSS. Okay, that's the very easy way. You don't have to beat yourself to study linear algebra even to identify good QSS species. I guess if I explained this in my paper years ago, maybe a lot more people would be using this this method to find this. Okay, so I guess we can take a 5-minute break. Okay, it's a good time to we come back at 4:15.
Yes.
Okay. Yeah. All right. Welcome back, everybody. Let's continue. Okay, so the remaining part will be a lot easier to follow, I guess. The reduction, all the reduction part. Again, we don't have a lot more very exhausting mathematics to discuss anymore. So I just want to show you some result about if you assume some bad QSS species, so the consequence can be significant. Okay, so for example, in early days when we deal with reduced model for methane, so typically we try to be very aggressive and include some species which is marginally good QSSA. Some are not even radicals, are quite a stable species. In that case, for example, if we assume this guy, which is it's methanol, right, and CH2CO. In that case, if you assume these guys are called a steady state species, so I was calculating in the 1D flame. So this is 1D premixed flame for methane. You see the red line. This is temperature profile. In the reaction zone or the post flame zone, when temperature is high, you see this guy's error. This is normalized error. Okay, the error is rather small, acceptable. Okay, but in preheat zone, it gave you temperature low. Then this guy obviously is not a good QSSA. It gave you error by 2 order of magnitude. So if you get unlucky, your code can even crash due to these huge errors. So a lot of cases, so there's a heavy price to pay if you assume the wrong guys to be QSS species. Just try to stay on the safe side. Okay, that's the lesson I learned many years ago. This one I talked about already. Now let's look at some real cases. So, in many years ago, when I developed this method to identify QSS species based on projection matrix, we can specify error, right? So the error basically tells you so what is the percentage involvement for this guy in the slow space? What is the percentage in the fast space? So we have this kind of percentage to compare with the threshold error. We call it error. If you only had like 1% business to do with slow business, we think it's good QSS species. Okay, so there, based on this one, we plotted who is what. Okay, you can clearly see many species has only to do with the slow space. So these are stable species. Okay, some guys always stay in the fast species. So that's actually a very good nature for radicals. Because they are radicals, actually there is a very small gray area between them. You can clearly find somewhere just to cut it. Okay, so fast guys, slow guys, easily find subset. But if you find something marginal, for example, O in this case, how do you handle it? If you want to be more aggressive, you include it as QSS species. Okay, but if we try it, we find you get 20-30% error. But is it worth the effort to assume one more QSS species and get extra 20% error? The answer is obviously no, right? So therefore, we always cut from here, basically. So we assume this absolutely good species to be QSS. Everything else, we still solve ODE for the remaining part. Okay, that's the strategy for identifying QSSA. the bottom line, the message you want to carry back is if you want to find a QSS species, stay safe. Just get this absolutely good ones. Okay. For heptane, it's similar. For heptane, you find most species are always slow. Okay. Some are always fast. There are a few of them in the gray area. So we want to fall in the safe side. So here we cut here. That's what we did. And if you want to be more aggressive, we cut here. So rather than 13 species, you get a 1, 2, 3, 4, 5. You get 18. So 13 species versus 18 QSS species. You remember for heptane, we get around 80 species, right? And the reduced model, if you have 13, it become about 67, okay? If it's 18, it become 62. Is this a huge difference for safety? It's not a huge difference, in my opinion. So therefore, being aggressive in identifying QSS species is really it's not a good idea. Okay, so right. And this one is basically what I talk about. So it's a masterpiece of my work. I think I always feel being proud of how to solve the QSS equations analytically with very low overhead. So eventually, but all the math here is very simple. You identify the subsystem, right? In the Jacobian, you find all the large entries, whatever. And then you only keep the large entries. You form a subsystem, which is still very sparse, actually. So this system can be solved. Actually, you can use brute force solution like this or B. So basically, you can solve with Gaussian elimination or any other method you call LAPACK to solve this. Or what you can do is you can take advantage of the sparse pattern in this coupling, because the QSS species really have a very sparse coupling, and you can solve this. Actually, you can derive the formula what each should be. So I use graph theory. Use the computational theory Google used to rank the different web pages. So I use PageRank. Use many very fancy advanced stuff. You can imagine that's more than about 10 years ago, right? And that's why I feel good about it. And eventually it works, actually. It really works. And it gives you this analytic solution, what each species should be equal to. You just don't need to call Gaussian elimination. You don't need to do iterations to solve it. But the whole thing, it just kind of complicated. Okay, when you read the paper, you feel exhausted, like what you feel right now. Okay, so I will just skip the details. But the bottom line is, if you want to spend more time to derive equations and to write them in MATLAB or whatever thing, and let the program to derive something for you, to take advantage of a sparse pattern, whatever method you use. Okay, you feel kind of satisfied. Okay, you feel happy to get something done. But if it's getting too complicated, maybe not too many people want to use it, because if it's too complicated, it's just more difficult to use. Okay, but the resulting reduced model is a different story. People like to use the resulting reduced model, but they don't want to use the tool. So that's why till today I still need to work on the reduction myself. My goodness. But if people like to use the tool, they will just derive easily by themselves. Okay, that's the lesson you learn. So if you want to look at how this subroutine look like, you can just look at this equation. So yeah, I just skip this. It's too complicated. And the basic idea, how you can solve this AX equal to B. If you have the equation AX equal to B, if you want to solve this equation, you do LU decomposition, right? So or Gaussian elimination. So that's what we do. And the cost to solve this one is order of n cubed. So basically solving a full Gaussian elimination, it can be still time consuming if you have a lot of QSS species. But the good thing is, first of all, you don't have too many QSS species to solve. So therefore, n is small number. Typically for n smaller than 2050, it's never a concern about solving this equation, whether it's analytical or just use a Gaussian elimination. So if you don't want to write whatever advanced technique, you can just call Gaussian elimination. You find that your overhead is very low, actually. Okay, solving this sub-equation of QSSA, it doesn't really take much time unless you have more than 100 QSSA species to approximate. That's a lot. So I almost never met a case you need to solve more than 100 QSSA species. So therefore, if you don't spend a lot of time, you're not that into the computer programming stuff, just call LAPAX to solve this. But if you are interested to play with the thing, to get it trained for this programming or graph theory or whatever, this is probably a method you can look into. So how to solve time for this kind of n-cube algorithm, like ax equal to b? What you can do is if you can decouple the different equations. So how to decouple the equations? Well, I mapped all the equations into a graph. Okay, in the graph, basically, if you need to solve one variable, the equation always, each equation couples several different variables. Okay, so by looking at different variable, you see if I want to know this one, that equation tell you you need to know the other one. Okay, this equation need to know the other one. So the solution for variable always depend on information for other variables. What you can do, and then this dependent, you can convert it to a graph. And this graph, a lot of cases, it's a sparse graph. And what you can do is you can use something called a topological sort. The good thing for topological sort is it can identify the strongly coupled stuff. For example, here you get 3 groups. Each group are strongly coupled ones. That means it's implicitly coupled. Everybody need everybody else to be solved. Okay, but if you can identify the group, for example, you call this to be A, okay, this B, this C, you find the requirement between groups. A only need B to be solved, okay? B only needs C to be solved, and A also needs C. Then you see there's no circles of the requirement. What you can do is you can solve C first, because C doesn't require anybody else. So group C has one variable. So this x6, you can solve it first, okay? Then once C is solved, B only requires C, and B doesn't require B, so you can solve B next. And then once B is solved, you can solve A. So you can break down the big system to small pieces, and you can solve them part by part. And each part, because of the cubic function, it makes overall cost much lower. That's the part for using graph theory, how to simplify or reduce cost for solving QSSA equations. It's a lot of fun to play with this. If you like computing theories, you will like this one. But if you don't bother, just skip it. Okay, and here is a example for real thing. So it's like for method case. For method case, when we map this graph to different groups, for this special group, because at that time I don't have a lot of reduced model to show. Unfortunately, this one, it doesn't show a lot of groups. Basically, this tells you one strongly coupled group have 9 species. There, for method, there are probably 13 different groups. Somehow I didn't show from the other one. It just show you one real life example. So this example is bad because everybody is strongly coupled. So you basically just cannot get rid of anything from here. But we have other examples. Basically, you can divide this into 3 or 4 different groups. So typically, you can divide a large model into about 5 to 10 subgroups. So overall, it can save some time. Okay, it's something you can look into if you are interested. This one, it's like solving the if you have this big kernel to solve, you get 9 strongly coupled species. So what I was trying to do is further to minimize computation cost to solve this mini kernel, like ax equal to b. So these 9 species form a 9 by 9 matrix, right? This 9 by 9 matrix, I'm thinking, can we just solve this even faster? Because why? Because A matrix is sparse. Okay, if you get a dense A matrix, what you do to solve it is use Gaussian elimination or LU decomposition. Okay, there's no much you can do to speed it up. So just the dense matrix multiplication. But if you have a sparse matrix, what you can get rid of is what you can get away with is you can use the method we learned in high school. It's called elimination of variables. Basically, you substitute one variable into the other, and you can get rid of one variable and one equation. You do this recursively, eventually you reduce everything to one equation, okay? And then you solve this equation, and then you back substitute everything to the other equation. So this is the solution for a set of linear equation by elimination of variable. We did this in high school, right? But can we do it automatically with computer code? Because if you can do it, it's more efficient than using Gaussian elimination, although it's mini kernel. Okay? So what I was doing is I found, because our experience is if you want to eliminate a variable, if this variable involves everybody, if you get rid of this guy first, your equation suddenly become a law. So you want to eliminate those unimportant variables first. So then everybody else, the equation gets not that too much longer, okay? So for example, you get an equation here, equation here, equation here, equation here. You get rid of this equation, this one suddenly become longer. That's bad, okay? So you won't get rid of the equation, get rid of the variable, which has the minimum impact on the other equation. They are remaining short, okay? So there must be different sequence, which one you eliminate first, which one you eliminate next. And this ranking, how do you rank it? So I was thinking, what can we do? How about we think of the coupling? If this guy has connection with a lot of other guys through one equation, it must be something important, right? If you think of the analogy is similar to the websites. So if the website is referenced by a lot of people, it must be an important website. And when you Google something, why Google put some website on top? Because many people are linked to it. But if you have a large network, how do you give a rank to the system? It's actually an eigenvalue problem. So you do the eigenvalue problem, you can rank the importance for different websites or different species. And then this rank give me something called the importance, or we have index, like how to rank those species, which one should eliminate first. So those unimportant ones, which connect to very few people, we eliminate first. So then the equation expand more slowly, right? So then we use PageRank to do the elimination. It turned out actually this works very well because I sampled the random sequence. The random sequence can give you different. So this is how many operations this number of operations you will need to spend. Like I randomly generated the sequence of which one to eliminate, and then compare with the one based on the Google PageRank. It turned out it almost always the best options, okay? because the computational cost using PageRank is always minimum compared with the other random sequences. And this is a histogram distribution, like PDF for the sample, but it doesn't matter because the method we use is always on the corner. Okay, it works amazingly well. It just tells you if you are just want to make little things a little bit better. Sometimes you can use very interesting fancy tools, and sometimes you need to spend a lot of effort, do a lot of extra work to make a little bit of improvement. And sometimes this improvement even doesn't make big difference. Okay, so it makes the method much complicated, but the product quality is of course good. But the side effect is people don't want to use this method because it's too complicated. All right. All right. So that's pretty much all the thing we show for the reduction. And here is just an example for showing if you want to compare the reduced model for inhabitant, like what kind of accuracy we can get by combining the skeletal reduction, DRG-based reduction, sensitivity analysis, and also the timescale-based reduction. You can see, compare with detailed chemistry, which is all the lines, and reduced chemistry is symbols. You can see the agreement is very good, okay? Both for PSR, for auto-ignition. So this is similar to all the other models we developed over years. So it's really a method. It doesn't guarantee you always 100% get a working model, but the chance is the majority of time, like over 95% time, you will get a very good working model using this method. Okay. And this is a comparison in 1D flame, including temperature and also species concentrations. It tells you typically what kind of error accuracy you can get from this reduced model. The next section is something very interesting, which is its idea or concept become very important in the recent few years. It's called reduced development. It's like a Haikam method or Haikam model for real fields. So this work is primarily done by Professor Hai Wang at Stanford. The Haikam model basically it has been like a focused on high temperature applications, like jet fuels, for example, or propulsion applications. It can also be used in some IC engine application involving low temperature chemistry. So I will just talk a little bit about the idea. This is a very, very effective or highly useful concept to bring down a huge detailed chemistry, like with thousands species into much smaller one, involving only about a little bit more than 100 species. So this is probably one of the largest reduction extent that we can ever achieve. Okay, and the accuracy is still very good. So the idea behind Haikam is you all know about a bit decision, right? So when you have a hydrocarbon field, for example, transportation field involving alkane or isoalkane, so the first step to initiate the chain reaction is always H abstraction. Previously there's H. So somehow through collisions, for example, this H was knocked off and then it's gone. You have this radical here. And once you have this radical side, the beta side, like one step, two steps away from this guy, the bond energy magically get significantly weakened. Okay, when the activation energy get weakened, it's much more likely the bond will break from here compared with any other possibilities. So once it breaks from here, you get a C, and these two will connect to give you ethylene. Okay, you get an ethylene together with a shorter radical, R dot, shorter alkyl radical. So this procedure can repeat, and when this radical side form, you get this weakened. So you shed another ethylene, then this get weakened, you shed another ethylene. Sometimes you can form propene or other intermediate species, but the dominant stuff is ethylene from beta station. Okay, this scenario happens most importantly at high temperatures. If you get high temperature application, let's see temperatures above about 1200 Kelvin, the beta station really become very important in a lot of combustion processes for fuel molecule breakdown. So the scenario for the breaking down or shedding for ethylene is almost similar to our experience of breaking a piece of glass. Okay, if you get a piece of glass, it's whole big piece. You can use some kind of diamond saw, maybe cut it smaller pieces once a time, and then slowly make it smaller. But the easiest way to break into small pieces is just use hammer to knock anywhere at one point, just like not get rid of one H from this glass, and then suddenly it shatters into small pieces everywhere. So this is a similar story. Now the whole point here is for our applications, if you want to simulate jet engine applications, do you need to resolve all the detailed process of huge molecule, big molecule, break down, shatter into small pieces? This happens in very short time. At high temperature, this can happen within, be measured by microseconds, typically much faster than the rate controlling combustion process. For example, than CO formation or CO2 formation. So the fuel cracking typically is faster than heat release process by several orders of magnitude. Okay, now if you don't care too much how the glass breaks, like what is the intermediate step the breaking happens, you can just model it. Okay, to see when the glass is broken, what kind of pieces, okay, how many small pieces you have, how many intermediate pieces you have, how many larger pieces you have. You can statistically get the product of the glass breaking. Okay, and people call it this field cracking product, or you can call it like the fragments of big molecules. But it's a soup. It's a pot of soup with statistically different molecules mixed together. The major components is ethylene, with a lot of propene, with a lot of methane, with a lot of isobutenes or 1-butenes, whatever. So, but there are a few dominant species with high concentrations. A lot of others are with very low concentration. You probably don't need to bother to know how much you have. So you can just figure out about 6-7 major species. What is the major product for the breakdown process? And then you can model this field cracking process with quite good accuracy. And it turned out with this kind of field cracking modeling, by skipping all these intermediate steps, the field breakdown, you can actually capture many high temperature flame behaviors quite accurately, including flame speed, flame extinction, burning rate, stir reactor, flame anchoring. A lot of them can be done with remarkable accuracy. Okay, so therefore, Haikam really is a wonderful tool we can have for this model reduction or to develop real field chemistry. So if you look at this 1D flame, so this is from the published paper on combustion flame. The major idea is why the field cracking process would not affect too much of the flame behavior is because the field cracking zone, as we said, it happens much faster compared with the seal formation. Seal formation happens mostly here, okay? Seal formation happens in the flame zone, and the CO2 formation afterward. So from here, CO2, CO heat release, and water is mostly formed here too. But before temperature rise high enough for heat release to be important, at here, but let's see if around 1400 Kelvin or 1500 Kelvin, this temperature is already quite high for field cracking. The beta station became exceedingly fast at 1400, 1500 Kelvin. If temperature even a little bit higher, the field just cannot survive those collisions. It will quickly break down into small pieces. So therefore, the pyrolysis zone, if you look, it's always before the flame zone, and the two zones are decoupled. So by 1500 Kelvin, where reaction doesn't really start yet, the heat release doesn't really start yet. So heat always was mostly from the back diffusion from the hot product zone at this temperature. Okay, heat release not that fast here, and in that case, the field cracking is already almost complete. Okay, so if you look at the field, this is the field concentration. By the pyrolysis zone, it disappears. No more field. Okay, what the reaction zone says, all the product like ethylene, propene, methane, all this kind of soup, it being carried into the flame zone, the reaction zone, and it controls the flame dynamics. Okay, so this is an observation why Haikam can save it. So this illustration shows what you can do, so basically to use Haikam to reduce it. So what we do is we model this pyrolysis part. Okay, once it's pyrolysis modeled, you get like several semi-global reactions. I will show you the detailed form next to give you what field to form what product from cracking at what rate. Okay, once you have this very few steps to give you cracking product, the remaining part it only involves small molecules between hydrogen C1 and C4 species. So this oxidation core is about 100 species in order of magnitude, together with the fuel. So that's how much you need to worry about in your transport equations. Okay, so how much like let me go here. So how many species you can reduce from this? So give you some kind of this give you a little bit of estimate about how many species you can reduce from here. Okay, so for example, if you get a large fuel, I use a 2-methyl alkyls. This is typically a surrogate mechanism for jet fuels. Okay, you can also use this for diesel or maybe what other diesel fuels even. Okay, so if you get this detailed chemistry. The detailed chemistry have 7,000 species, 30-something thousand reactions. And if you look at them, most of the species are the intermediate product when the large field break down and break down from different locations. And different intermediate species can break down also from different locations. So the combinations give you the exponential. So basically you get a kind of exponential function as the number of atoms in your molecule. If you get a larger molecule, your mechanism grows up dramatically, okay? So in this sense, so basically, majority of this large molecules here are the intermediate species during the molecular breakdown, okay? And if you can model the whole part, you just need to worry about the C1 to C4 species here in the corner. So it can really give you a factor of like almost 50 or even more reduction. Okay, it's larger extent than any other method we have ever seen. So this is really useful method basically you can have. Okay, once you have this one, then the question here is so you get this ratio between different cracking products. Are these cracking products the ratio stable for different applications? So the story will become a lot more complicated if the ratios, for example, how many ethylenes you have after production. So therefore, this coefficient, can it be approximated by some constant for almost all different flames? It turned out that this ratio can be very reasonably approximated by a constant. And because if you think you break down glass, you try different glasses, they break down, they're really statistically somehow they're determined by molecular structure. if the breakdown process is heavily depend on molecular structure, the final product concentrations or the compositions indeed have some statistical ratios you can determine by measuring from experiments. So from shock tube experiment, you can track how much ethylene was produced, how much methane was produced, and then you get a ratio at different locations. You can statistically get an average like coefficient what this is. So then you can put together two sets of equations. The first reaction is the field. The field you don't have the concrete formula because it's average molecule. How many carbon, how many H on average you have. It can be blend of species. So you can have several hundred different components, but all appear all the same. But when you put them together, the product always has, for example, ethylene, propene. This is butene. Two different structures for butene, and then some aromatics give you the aromatic rings, okay, or toluene. So this is a methyl radical. So these are major ones you need to worry about in the field cracking product. And the first one reaction is thermal H abstraction. So if you have a field molecule with RH, how do you get rid of the H in the beginning to initiate the beta station? When temperature is high, you can just break it by molecular accretion, right? That's this one. It's therefore through molecular accretion, thermal accretion. Okay. Another way is if this guy see another radical, if another radical come here, it can take away this H. So it can grab H away and leave this field to be radical to start the beta station rule. So this R can be H, can be O, can be OH, can be a whole bunch of things. So R here, therefore you pick the major radicals in the radical pool. So there are not too many of them, six. I think 6 of the different major radicals you need to worry about. It's a H, methyl, O, okay, OH. So these are not radicals. O2 you need to keep it there because O2 is some kind of funny molecule. It's a sticky molecule. It's oxidizer, right? At lower temperature, O2 can grab H hardly from molecule. At high temperature, O2 is not important, but at low temperature, when you don't have a lot of other radicals, O2 plays the key role to do H abstraction. So you need to keep O2 there too, and HO2 at lower temperature. So you keep 6 guys for the H abstraction by radicals or kind of a reactive species, and 1 for thermal accretion. So this 7 steps actually completes the field cracking process. It's a model. It's a model, okay? And the coefficients, you get a whole bunch of the coefficients. How to determine the coefficients? You need to use the element conservation laws, right? Carbon, H, nitrogen, whatever is always need to be conserved, okay? And secondly, then the ratio between each other and how many more information you need, you do experiment measurement to measure the ratio between each pair of species and use those measured ratio to determine the remaining parameters. So therefore, together with element conservation and measured branching ratios, you can determine all these parameters in the cracking. So that's the idea of a Haikam. And then after you get a detailed Haikam model, amazingly we can apply further reduced model for it. Okay, you get it because there is still some kind of unimportant reaction species in the C1, C4 subcore. The C1, C4 chemistry, it's just like you can reduce ethylene or reduce methane or reduce propane mechanisms. Okay, so we run scalar reduction, we run timescale based reduction. Eventually, we can reduce from 120 species, which is detailed Haikam model, to much smaller, to less than 30, 40 species. Okay, and amazingly, the agreement is still very good. So eventually, this tells us with Haikam model, we can get away with a quite comprehensive and accurate reduced model for high temperature applications with only about 30, 40 species. That's probably the smallest we can get compared with the previous approach. If we start from a fully detailed model, so no matter what we do, eventually we get for more than 50, like 100 species. If you get a dodecan or larger molecules, you probably need more than 100 species in the reduced model. Okay, so Haikam eventually the reduced model was probably around half of the conventional reduced models. So that's a dramatic reduction. And here's the question. So how are the reaction rates determined for the equations? Oh, that's a good question. Thank you. Let me go back to this equation. The reaction rate actually is how fast the hammering happens. Now, if you want to break glass, how many pieces of glass you want to break is how many field molecules you want to break, right? So the first rate therefore depends on collision rate. So it's same reaction, the field collide with whatever third body. So you compute this frequency, collision frequency, together with what portion of the collision is strong enough. So you involve this Arrhenius term with the exponential term. So basically it's collision frequency, let's call the collision frequency, let's see, you C times the P, right? The probability, which is the exponential of negative E over RP. So the chain initiation reaction, actually you can get this rate actually also from detailed chemistry. So if you get a fully detailed model, you see how fast the field molecule collide with third body to get H abstracted. So this determines the first reaction. The second reaction is how much field collide with H. Okay, if H radical collide with field, what is the rate? So how fast the first H is abstracted, it rate controls, rate limits this model. Basically, the first H is gone. The glass is broken into small pieces. So that's the assumption. Okay. Okay. All right. So here is the example of what we can do. We reduced the Haikam model for two jet fuel mixture. A2 is a conventional jet A or JP8. You all heard about JP8 for military and jet A for airlines, right? So this A2. A2 means the commercial jet fuels. C1 is one of the candidate alternative jet fuels. So people made this fuel from bio source. So people want to figure out if you want to blend bio jet fuel into real fossil jet fuel, what kind of flame property will change, how it can affect this jet applications. So we need to reduce different reduced models to account for the blending for the two different jet fuels. So eventually we start from a Haikam model, contain both jet fuels, and the reduced one only has 39 species. And it accounts for different concentrations for the blending. So that's quite impressive. even to myself. Okay, so you can validate the ignition delay times, stir reaction, and flame speed, and also we did a counterflow extinction, counterflow premixed and non-premixed flame extension. We tried everything we can, make sure this reduced model replicates whatever we can do for detailed chemistry, to just to make ourselves more more comfortable in releasing the model. Okay, and then this figure shows actually the blending of the two fields is very interesting. You know, A2 is dominated by this linear alkanes or normal alkanes, and C1 are more comparable to isooctane in engine fields. It's highly branched alkanes. So therefore you blend A2 plus C1, it's as if we're blending this PRF field for gasolines. So therefore we have this crazy idea. How about we blend A2 and C1 to make PRF fuel for jet? Indeed, if you change the concentration for C1 in the blend or the isooctane blend, you can get a different kind of CT number or different ignition delay time. So for example, these are the different concentrations for how much blending you have, right? So you can see you can have a dramatic difference in ignition delay time. So for flame speed has a very small difference. Is from 28 to 30 centimeter per second. The difference here is not a big deal. Extinction has a little bit difference, extinction for flames, okay? But the ignition delay time is more dramatic. But keep in mind, this is a log scale. Everything else is a linear scale. So the dramatic difference you can make is if you have a jet application which is sensitive to ignition delay time, you add biofuel to it, like C1, it can affect your application dramatically. So you need probably redesign your engine. But if you're burning your fuel like a stir reactor or a spark ignition type, you probably don't need to worry too much about the difference. You can just blend the biostock into it and then let it burn. Okay, so that's a good thing for, and we discussed in the beginning. So if you have a stir reactor type of application, it's not really very sensitive to fuel structures, whether you have linear alkane or you have branched alkane. As long as the heat release is the same, then everything else is similar. So it burns everything you throw to it. Okay, so that's a good thing for continuous flow combustors. But if you design your engine in a compression ignition manner, you depend on auto ignition to work, then you will have big trouble. For any new fuel you have, you need to beat yourself to measure the ignition delay time, or you need to know the CT number, you need to know the octane number. That's so in this sense, I guess, if possible at all, you design your engine like a jet engine. If you have to use your engine like in the IC engine manner, use a spark. Use spark can save our life a lot. Okay, so compression ignition like HCCI type, we're just beating ourselves. So that's my opinion. I guess that's probably why it's so difficult to move HCCI. And later people still, in the end, I guess a lot of people still add spark to HCCI to control the ignition delay time, because it's just too sensitive to the fuel structure. Okay. I guess that's, yeah. So this one tells us, so Haikam model actually can also be graphed with reduced or lumped semi-global steps for NTC steps. You know, previously the number of Peters developed like a 10-step, about 10-step lumped steps for NTC chemistry. So what we can do actually is we can use this semi-global step model to mimic the low temperature ignition chemistry also. If that happens, maybe we can also extend this Haikam model a little bit to account for some of the ignition, like low temperature ignition problems. So in that case, the low temperature chemistry all need to be fitted. You need to fit it against different fuels. So every time you get a different new fuel, you need to fit the parameters to make sure they give you correct low temperature ignition delay time. Okay, so that's the story. But that's fitting. It's not a quite a fair stuff, because the application has some kind of limitation. You need to make sure when you want to ignite the field, you compress it and let it ignite by itself. You don't want to have mixing. If you have mixing involved, then the fitting model may not work well. That's some warning from me. So the semi-global fitting model for NTC steps, it's supposed only should be used for the real. My goodness. It's supposed it should only work for really auto ignition. You don't want any mixing process to disturb your ignition process, because the fitted simple model really is not capable to capture this complicated cases with mixing. Okay, but again, you can add about 10 more species, so it takes care of the NTC step. Looks like it can handle low temperature chemistry a little bit. But also you can add NO chemistry to it. You can add a pH chemistry to it, like soot chemistry. The good thing is NO chemistry and the soot chemistry are all depend on high temperature part. So it's not very sensitive to low temperature chemistry. So therefore, Haikam model is very suitable to be combined with NO chemistry with pH chemistry. And then when we combine them, we can also run through the reduction process. Eventually, if you look at what we did for the reduced model, we developed Haikam models for many different fields. Okay, for conventional, this is conventional jet fuel for the airlines. So this is biofuel, two biofuel, and this is mixture for conventional fuel and biofuels. So this is the new biostock, and this whole bunch is with NO subchemistry, and also we did one with pH soot chemistry. Okay, and there are also two versions for rocket fuels. The RP fuels are the rocket, the propellant. So basically, we try to, and we have some other thing, not listed here. We have GP10 if you want to try, and we have two gasoline fuels, like a Shell, two Shell gasoline fuels. So not listed here. But if you go to the website, so Haiwan's website has all the detailed and reduced models together with subroutines you can use. If you are interested in trying this reduced model at all, you just go to their website and download it. So after reduction, you see without NO, without pH, so the reduced model has less than 40 species. That's remarkable, okay? And with NO, it adds about 10 more species. So that's how much you need to account for NO. So this NO includes both thermal NO and prompt NO, okay? So it's a rather comprehensive NO chemistry here. And with pH we don't have the really perfect pH to use. So this is just for demonstration. If you have a pH, so we use the pH from cost. So the cost Mac has a pH subchemistry, and then we just combine that one with Haikam, and eventually after pH chemistry is about an additional 100 species. Okay, additional 100 species put together, it's like more than 200 species. After reduction with soot model, let's go to about 60 species. And this level of reduction is already feasible. It's okay for, I will say, most safety applications people are doing today. Okay, both RAS for LES, even for DNS, with 60 species is already fine. If you have less than 50 species, people are doing DNS today routinely with this kind of chemistry. Okay, and that's the story. Oh, we have another question. Just to clarify, Haikam with NTC should not be used for cases with mixing. It should not be used for cases with strong mixing. If the mixing can disturb the ignition process, because this model, semi-global steps, because not only for Haikam, we have semi-global steps in other mechanisms also, okay? If you want to simplify your low temperature chemistry, you lump a lot of reaction steps into 10-step semi-global steps, and those models are fitted against auto-ignition process, okay? If you get a mixing coming in, so for example, if the ignition occurred by 50%, but the mixing happened, drag it back, mix it with a fresh mixture again, this will break down the whole story, okay? Because the model, it's a fitted model, cannot handle too complicated situations. And the mixing will just give you all different kind of surprises. You can always design the process with mixing or break the model. That's why I tell you. So, but in many cases, if you have a cylinder, like a rapid compression machine, you compress it and let it happen, and no much disturbing, it's probably working well. Okay, that's why for a lot of compression ignition engines, actually the lumped semi-global model, it works quite well, reasonably well. But you keep in mind, there are cases you can design to break those models. Okay, so thank you for asking this question. And the last part I want to briefly mention about this model reduction business is a lot of people, including myself, okay, my own group, when we do the reduced model, we always want to make it as small as possible, or even smaller than we can do. I always get requests like, can you make your reduced model only half the size? Right now you have 20 species. Can you make it 10? Or can you make it 5? You know, because you keep on getting this request. Sometimes you get annoyed, but if you think you want to make it smaller yourself too, right? What if I over reduce it, like from 50 species to 30? And after you remove 20 important species, okay, there must be consequences. So you messed up something. Can we just tune the A parameters, like the rate parameters, to pull it back? So that's a lot of questions. Actually, if you look at the literature, in many papers, people do over reduction. The benefit for over reduction, you get a much smaller reduced model, right? Rather than instead of 50 species, you get 20 species or 25. But we tune the A parameter to match some ignition date time, flame speed. Even for 20 species, you can still get several hundred rate parameters. But several hundred knobs to turn can give you a lot of flexibility to fit a lot of things. So can we turn the knobs to tune the mechanism, make it work for a lot of things, and get a good reduced model? So I tried it myself. Okay, if you look at this one, we developed the N-Dodecan model. So this work is actually done by Tong Yao, who was in Tsinghua University, who was visiting me a few years ago, and he worked with me to first of all, at that time we don't have Haikam, but we have a prototype of Haikam. So basically, he compiled a prototype of Haikam model for N-Dodecan, together with some kind of together with some kind of other updated things from literature. So eventually he constructed a skeletal model for N-Dodecan, okay, with 54 species. Okay, he did some kind of a semi-manual reduction. So he put together a whole bunch of reaction groups together. So it's a small model in the beginning. And then we identify for the steady state species, it can be reduced to 37 species. And keep in mind, this is only this is only for whatever you can use for Haikam models. Okay, it assumes the field cracking is fast. It gives you the product. Okay, it's not fully detailed stuff. If you are interested in what happens in the field cracking process, so don't bother this one. But this model is already much smaller compared with many other things we have, because all the previous reduced model we have for N-Dodecan has more than about 100 species. Okay, so it's only half the size. If you don't do anything, you do the validation, you find it doesn't agree with a lot of data. So what he did, he spent several months, because without tuning, see, if you put together without tuning, it's here, and then he tuned the parameters. He found which parameters should you tune. How do you tune? You run sensitivity analysis to see which knob give you the change. Okay, if it give you change, you turn it. So you pull this down, and this is ignition delay time for different pressures, and then he tuned for a lot of different things, even including real engine simulations at Argonne. We collaborated with the Argonne group, so we simulated some kind of ignition processing engines, in diesel engines, and try to tune it to fit what happens in the diesel engine. So we tried a lot of things to match many targets, as many targets as we could ever find. If we have experimental data, we include them. If we have detailed chemistry, we try to use detailed chemistry to compute whatever we can compute, okay? We try to match everything. Eventually, it seems we get a tuned model, which really works, should work pretty well, right? But then the thing is, after a while, so somebody tried engine simulation for a different case. They find that actually the model over predict a lot for some new situations. So we spend a lot of effort to tune this model. But why for new cases, it will give you larger error. so we thought about this for a while. It turned out the tuning, this is the nature for tuning. The tuning process is if you have a knob to fit a lot of things, okay? It's just like if you have data points. If you have one line to fit it, you just have two knobs to turn, right? So you cannot fit every point, but your model will not give you too much surprises. But if you have a very complicated model, like say you have polynomial with 10 terms, so you have 10 different models, 10 different knobs to try to fit this data. You can manage to let the curve fit go through every point, okay? But if you get a new case here, it will give you a problem, right? And this is a well-known problem for so-called overfitting. Overfitting means you get too many knobs to turn to fit limited targets. Okay, it's simple like that. So far for all the detailed chemistry and the reduced chemistry tuning, unless you are using like a 3-step model, 2-step model, you can strike through all data points. You can only fit for like a flame speed alone or ignition delay alone. But if you get like a regular reduced model with 50 species or 100 species, the chances you get hundreds of knobs to turn. You always get overfitting. Overfitting not only can give you errors where within your reduction range, it can give you even worse error if you go out of range. It can go totally wrong. So the experience is if you tune a model, particularly using this automated tuning process, okay, the chances you can make your plot make much more beautiful compared without tuning. But then if you have new cases, you may get an even larger error than the untuned model. So the tuning actually doesn't really remove the errors. It just hides it. It hides it for the points you want to see, your target, but it's buried somewhere else. And if you hit that point, you'll get in big trouble. So mathematically, I try to prove what happens here. So I just don't want to bother you too much Friday afternoon with mathematics. What happens here, you expand this tuning process. Eventually, the only possibility you can make sure if you apply or reduce tuned model to new cases, when it can be used. So there's a requirement. It's a sensitivity for the new application. The two means a new application, it's not in our tuning, okay? For example, you are simulating a new type of flame. And this flame parameter is sensitive to a bunch of reactions. You know this tooth-like sensitivity pattern, right? This is sensitive to this reaction, that reaction. So each tooth is a reaction. This pattern must be the same, or can be linear combined through the pattern you have for a target. So that means you shouldn't have any flame which give you different sensitivity pattern. If you get a different sensitivity pattern, then game is over. that means you will mess up the new simulations. So in this sense, the tuning, it's not a very pleasant to declare this, okay? Tuning doesn't really solve the problem. It will give you more problem, although it can make graphs feel more beautiful now. It applies both for reduced model and for detailed model. So a lot of people try to tune detailed model to make it more beautiful. But actually, if you detailed model is even worse. You get tens of thousands of knobs to turn. You can turn almost anything to fit whatever you want. If you only have ignition delay time to fit, you turn a million knobs, what do you think you can get? So you get a new case, you will find trouble. So that's why actually we figured out for even very complicated mechanism with a lot of reactions considered, you can easily the mechanism for different groups can easily fit ignition delay time. Okay, all very well. But if you try a different thing like PSR, you find huge difference. Okay, that's the big problem here, and we need to keep in mind. So if you can determine the rates without tuning, so if you want to give people a mechanism, try not to turn the knobs. Somehow, if you can compute these knobs, you know what this knob should be put, where it should be put, and don't turn it. So, and if this product, this mechanism can work well for many different cases, that means it's really high quality mechanism. And if you have to turn the knob to make it look better, that's only to hide the errors. It's only to hide the errors. Okay, that's the message here. And that's strategies to avoid overfitting. So that's the standard way what other communities like computer science or data mining community, what they can do to try their best to avoid the situations. Overall, if you don't have to do tuning, just don't do it. So that's the best way to avoid overfitting. If you have to do it, try to tune simple models rather than complicated models. If you have to do the tuning, do the model reduction, simplify it to as small steps as possible, like 4 or 5 steps, and then tune a 4-step model. So that makes a lot better sense than tuning those 100-step models. Okay, so tuning more complex models doesn't mathematically make sense. And also you can use the standard training, test, validation set. So that basically means you can tune the model, but when you do the training, you use 2 parts. You do the training on part A, and then you test the error on part B. If the error is not good, you can do the refinement, whatever, until you are happy with the model, but you use totally different subset to examine the quality of your model. So your quality of the tuned model should be dictated by what happened for it to predict a new data set. And this C data set should be different from A and B. So this is the standard way people in data mining, machine learning, how they can try to limit the amount of overfitting, okay, to make the chance of the success model better. All right, I guess because we got 10 more minutes to talk about advanced chemistry solver. That's a big part of the slide title, but actually there's not much we need to worry too much about this one. There's just one very important lesson I want to share with you guys about developing chemical solver, chemistry solver, stiff chemistry solver. What's the big deal between stiff chemistry solver and the model reduction? You know, the purpose for developing good solver is always to make simulation faster, right? Major purpose for model reduction also to make it faster. So you can achieve more efficient simulation using both ways. For model reduction, you design methodology for model reduction. As we said, you don't have to develop rigorous methods. The method can be good, can be bad, or can be even wrong. You can use any method to get a reduced model. As long as you validate the model and it passes your test, it's a valid model, okay? But solver is a different thing. If you want to develop a solver and let people use it, the solver has to be working. It shouldn't give you surprise. If it gives you surprise, that's not acceptable, okay? So therefore, that's the major difference between chemistry solver. So it's a lot more challenging, a lot more demanding to develop chemistry solvers. So you can apply a lot of aggressive approximations, try to develop this kind of fancy solvers based on low dimensional manifold or whatever. But keep in mind, a solver, if you want to really develop a solver, it should be rigorous. People should be able to trust it. If you develop something, sometimes works, sometimes doesn't work, you shouldn't call it a solver. You should call it another model or another modeling method. So that's the major difference. That for stiff chemistry, you all know the challenge here is for stiff chemistry, if you want to solve an ODE, dy dt, if it's stiff, my goodness, if it's stiff, you can use a very simple implicit solver to do it. Why? Because it's unstable, numerically unstable. I guess you all have this experience, right? You run a simulation. As long as you're running reacting flow case, you cannot use the forward explicit method. which is very simple to use. We learn in like freshman year. And what happens is you have to use the so-called implicit method. The implicit method means you have to discretize your governing equation to use this to be wiped the future step. Okay, you have a non-linear equation of the source term, and your variable after discretization, this variable is unknown. It's a future step. What should it be? And the left-hand side is basically yn plus y minus yn divided by delta t. Okay, so you see you have unknown here, and it's coupled by a nonlinear equation. Solving this nonlinear equation is no fun. If you have detailed chemistry involved, you have to use Newton solver. The challenge, you have to use Newton solver. Otherwise, other solver will give you all different kind of trouble. And using Newton solver, you need to compute Jacobian matrix. Jacobian matrix is very time consuming to compute. And you have to do Newton iteration. Iteratively, sometimes Newton iteration will give you divergence. So all sorts of headache. So reactive flow simulation means headache. Okay, so we all have this unpleasant experience. But that's why we always want to make sure we want to make improvement to solvers. Can we make this headache less, like better? Can we have better performing, like faster solvers, but still rigorous? Okay. What happens here is if you need to use Newton solver, the time it takes for Newton solver for small systems, if you get several hundred variables, so the cost is order n squares. Why is order n squared? Because it tends to take n squares time to compute Jacobian matrix if you do numerical perturbation. Okay, but if you get a large system with thousand variables or more than 10,000 variables, so it scales with n cube. So large system is a lot more difficult to solve for stiff system for reacting flows. Why is this? Because this n cube was from the Gaussian elimination in the Newton solver by LU decomposition, not LU decomposition, it's LU decomposition. Okay, LU decomposition gives you the n cube cost. So if you get a large flow field, every variable, every grid point, it counts as a variable, right? So you get a 100 species times, let's say 1 million grid points. How many variables you have in the flow field? You get 10 to the 8th. There's no such a possibility you can solve everything in the flow field implicitly. So how do you do the implicit solver? So that's not possible. Okay, so fully implicit solver for CFD is not possible with Newton. And then people say I can do iteration, but iteration you never can guarantee it converge. The chance is it doesn't converge. So there's a most popular scheme people use. It's called a splitting scheme. Splitting scheme basically means if you write down your transport equation, you have a chemical source term, you get a transport term. Transport term typically is not that stiff. Okay, the stiffness comes mostly from chemical source term. So splitting scheme says, how about we mimic the behavior for the system with a splitting step? Like we integrate an equation which involve chemical source term first. Then we integrate another one only involve transport term first. And then we combine them. So maybe we can get, so we get a contribution from here, and then we get contribution from here. We can combine the next step, right? Sounds to be plausible. And the good thing is that when we solve this system, dvdt is phi, chemistry is local. So you can solve each point separately. So you only have 100 variables for each grid point. So therefore, LU decomposition Newton iteration is not a problem. And when you solve this one, dφdt is transport. This is not stiff. You can use the explicit scheme, or you can use some kind of iteration if it's weakly stiff, just to quickly get the coupling of the flow field. And then if you combine them, it will work. Wow, you don't have to solve a fully coupled system. That's wonderful, right? And a lot of people in the flow field in the simulation actually using splitting because it makes it possible to simulate a stiff reacting flow. Now here's the question: is how good this scheme is? How good this scheme is? People always trying to to use this, but for some cases you find there are big errors. People call it a splitting error. Okay, the magic error happens here. It's kind of interesting why you always have splitting error. It means you split step, you get some error. It doesn't decay with your time step. And you get a smaller step, you still get the error here. This kind of error is called splitting error. And where is error from? Actually, a lot of people try to dig into it. And maybe most people don't want to dig in. If you find the problem, what would you do, right? You lost the method to solve the large flow field. Why don't we just use it? We know there is splitting error. But the first thing you want to figure out is where is the splitting error from? Why is there? So what happens is we look at a toy problem. We look at a toy problem here. So we identify where the error actually exactly was from. If you have the system with stiff chemistry, for example, together with some mixing, the mixing term here will make it really, really simple. We get a radical in the system. Formation slow, consumption is fast, and then there is one catalytic reaction radical can catalyze the field to form product. It's like two-step model to mimic this real chemistry, and then with a very simple constant input term. So you get a radical inputting to the system. And we try to use splitting, try to compute, okay? The accurate solution is here. So if you use fully implicit method, you get this solution from VODE. But use splitting scheme, you use a reasonably small time step, you get a large error. And this error in species concentration is order 1. It doesn't decay with your time step. That means you make your time step half. This error is still there. So what happens? Why it's like that? Now, what happens here is the radical. Okay, the radical, as I said, is some kind of very important thing for chemical reacting systems. Keep in mind, radical, you don't mess up with radical. If you mess up with radical, your reaction rate is wrong because radical is a catalyst. You definitely don't want to make trouble with it. Okay, so what happens in splitting is, if you have radical input, this radical, if you have an external source for radical, your reaction rate will be very different, okay? Because the radical consumption rate, if you have a radical coming in, it will quickly consume. How fast consumption will happen? It equal to the production from chemistry and the input from transport. So therefore, if you write down the concentration for the radical, what it should be? It should be the consumption rate. On top is chemical formation rate together with the input of radical from transport. Okay, so like in premixed flame, you get a back diffusion for each radical here. And what happens in radical is in called a steady state approximation, right? If you assume this input production and balance output and consumption, so the radical concentration is roughly here. This is the so-called called steady state concentration. But if you don't have transport, you cut the input source, the radical concentration will drop immediately. Okay, so the correct source should be here. But in splitting scheme, if you get rid of the radical input, the concentrations immediately drop to a different level because this part is gone. You only have a chemical formation. So with chemical formation, you have much lower concentration with the radical pool. With input, you have much higher. So with or without radical, the reaction is two totally different animals. Okay, the reaction rate is totally different. That's why the production rate for major species are wrong because you have a wrong radical pool concentration. Due to this reason, so basically for any applications, you have a back diffusion controlled reaction. And if you use operator splitting, you will experience a lot of trouble here. Okay, so therefore we find the principle here is for reacting flow. If you have mixing, when you do the chemical integration, you cannot get rid of transport. Okay, the simple story, short story is like this: do not split. But if you have split, you can fix your transport term to be constant when you solve your chemistry source term. So like for example, if you want to solve this, if you want to solve for this chemical subsystem, add a constant T term. Okay, at a constant term, you can still solve the local things as if there's transport there. But in case you have to make sure the transport is roughly constant. So there are different fixes coming out recently. If you look at the paper, people always starting to carry this transport term with different fixed version of stress splitting. Okay, but the story we learned here is, for a long time people have proved like a stress splitting. For example, the stress splitting give you second order accuracy. Why in reality it doesn't give you the accuracy you need? For example, let me see where. Let me just quickly go here. Okay, so here basically is what happens, stress splitting. So this is a cutting step. From here, if you use tiny small time step, your system is not stiff anymore. Okay, so this is explicit, almost non-stiff system. Here is time step is faster than radical time scale. You get a stiff system. So your error is almost plateau. It doesn't decay with your time step, the time step side. So this is so-called second order scheme, give you zeroth order performance. What will happen? Why people have proved it happened. It turns out when they prove what happened to the error, pay attention here, okay? Their error is proportional to some constant plus some h is time step size plus time a b c time h squared. You remember you can write down your errors in this kind of form. They can prove this term goes zero, this term goes zero. Okay, so then you get a second order term. I mean, this is basically the integrated error. So if you get an integrated second order over a time domain, that's a second order scheme. Okay, if you do each one time step, it will be HQ. But they argue nominally this is the second order accuracy term. Okay, the second order scheme. But what happens here if you dig into what C is? C involves Jacobian squared times something else. Okay, Jacobian squared, remember what Jacobian is for stiff chemistry? Jacobian has a large entry. Somewhere in the Jacobian large entry, it has a huge number here, okay? And this huge number, if it's squared, it's even larger than your h squared. So that's why this one is order one, actually. And the lesson we learn here is when the mathematicians try to prove it, they don't care too much about this stuff, the coefficient matrix for stiff chemistry. But when you try to derive the error, you always pay attention to the coefficient part. The coefficient part for stiff problem can have a large number there. If you get a large number there, you don't get the claimed accuracy. So the second order accuracy for splitting scheme, it doesn't happen for stiff problem. Okay, sometimes if you are lucky, you don't get this large number multiplied, so you can get a smaller error. But if you don't get unlucky, you can get a very large error. Order one error means arbitrary, any error you can get. So as a result, if you're dealing with a complex flow field, you can get any error. So that's the method to carry away. So be very careful when you use operator splitting scheme. Okay, so try not to carry it. So what we did to fix this is we developed a different method, just called AHI. But the AHI, the key message is don't split it. Don't split it. We carry the transport, but we treat transport to be implicit. We choose a short enough integration time. Time has to be short enough to make this transport term non-stiff. Okay, the only stiffness is in chemistry. So we just treat the chemistry with the implicit stuff. So we can make the performance much better. So this method is called HI. The HI, we can formulate a first order, second order, but the key message is don't split chemistry and transport. Okay. To make another analogy, is like a chemistry is like a cat in your room. Okay? A cat in your room. If you want to predict what cat is doing, you have to somehow have somebody to interact with the cat, throw him a toy or whatever. Okay, he will jump around. But if you want to have one moment with only the cat, another moment with only the toy, the cat will not jump. Okay, the chemistry will not give you the performance you expected when the two put together. So that's the story for splitting. And for HI, for the HI formula we developed, basically we can also take advantage of sparse matrix, use non-analytic Jacobian method and the sparse matrix technologies. Eventually we can make the solver quite efficient. If you look at the time cost for the solver, with fully explicit solver, it's like here. This is the case for fully explicit solver in log scale. Okay, so the best general solver out there, we call it LSODS. It's basically this one. If you use analytic Jacobian and sparse matrix, you can make the slope 1, which is a linear computational cost. And with HI, we can even make it even better. So basically, you can see HI1, HI2. It can go here. So these two circles. So it's about a factor of 2 to factor of 5 faster than state-of-art solvers out there. So, and compare with the time required to simulate, like to compute one single ration rate, it's only like a factor of 3, 4, 5. That means the time you need to solve this HI system is almost like an explicit solver, almost like an implicit, explicit solver. So much faster. Okay, but it's just need some more computational effort just to bring everything together. Sparse matrix, analytic Jacobian, all of the thing. Okay, so the bottom line, the message carry away for solver development. For stiff chemistry, it's a lot more challenging than we imagine. A lot of cases, when you develop like a stiff chemistry solver, always make sure you don't get surprise in your coefficients. You get a time step here. Make sure this guy is order 1. Then you can claim it's second order scheme. Okay, and I guess we can stop here. I use a few more minutes. I'm a lot. Thank you very much for listening. So it's really a big pleasure to have you guys here and ask wonderful questions. Thank you very much.
Do we have any more questions? What's so okay. Well, anyway, on behalf of all do we still have the phone? Yes.
Yeah, let me see the question here. So
that's a question. Yeah.
Source code which can be used to run PSR extinction problems. That's an interesting question. PSR extinction, typically you need to march along the S-curve. We have Cantera to compute one PSR solution, but to go to the extinction point, you need to use the previous solution as the initial guess to march step by step close to the extinction point. So I wrote a script to do this automatically, but it was for chemicals. So I not to publish this, but the controlling step is quite straightforward. And also, if you read a recent paper Yun Chao published on combustion flame, we got a different formulation. We modify the governing equation for PSR. It can solve the extinction turning directly. So that's a very interesting paper you may want to look. So a paper on combustion flame, you search my name and my student Yun Chao Wu, you can find how to solve the turning point for PSR directly. So you can probably even implement this code very easily. In MATLAB, it's just a few lines of code, very easy. Okay.
We have other questions? Well, it's it's very sobering actually. The thing is with combustion chemistry, on the one hand, it gets bigger and bigger, more and more complex chemical mechanisms. On the other hand, you have to use it, right? So you have to simplify. So to do that, you cannot just brute force what Professor Lu was emphasized to us. You have to have a good sense of the chemistry, how you simplify it, and also you need to know the mathematics and all that. So certainly there's still a lot to do, and I don't know what. Do you see any convergence? The mechanisms keep on getting.
Chemistry is really tough stuff. That's over this year. It's really tough.
Yeah.
you learn philosophies from working on chemistry.
Yeah.
You can understand a lot of things, how to make it like not only to do research but life. It benefits your life. Or a lot of the lessons we learn from doing this research actually also apply for how you make make a daily living on other field, like other aspects. Yeah, don't be too aggressive, for example.
That's right. That's right. So anyway, it's getting late, and then on behalf of all participants, we just want to thank Professor Liu again. Every time I hear him talk, there's always new stuff. He's not just he's making progress. And it's so anyway. We just again thank you very much. That as I said, I cannot with others. I cannot take you out for dinner. But you enjoy your dinner?
Yes, virtual dinner.
Virtual dinner. And then next, hopefully soon we'll be able to meet again. So anyway, I just represent all the participants and thank you and clap our hand.
Thank you very much. It's wonderful.
Yeah, thank you so much. Yes. Yeah. Okay.
Have a good weekend.
Yeah, you have a good weekend.
All right, bye-bye.
Bye-bye.